Let me present myself. I'm Alina Holcroft, and today we are going to understand quantum technologies. But first of all, I wanted to insist and to say more about why we need to interest quantum. Is the traditional computer limited in solving specific problems? What are the classic technologies need to build the quantum computer? And do we need to understand more on the link between the quantum technologies and other aspects as electronics, laser, photonic, and other application in transportation, in energies, finance, or marketing, or other artificial intelligence and research. So that's why today we are going to speak and to understand the use of the quantum technologies. And for that, I would like to present you, first of all, Isabelle Kuhn, which is the Executive Vice President Digital from Grand Est Region. And we are welcome to have her here today with us to introduce our event. So Isabelle, make some noise and say welcome to Isabelle, and thank you very much.
Thank you very much, Alina. I will do it in French. I apologize for that. Bonjour à toutes et à tous. Il me revient de lancer cette matinée. Je vous prie d'excuser Pierre Grussenmeyer, le directeur de recherche de l'INSA, qui est quelque peu bloqué dans son voyage en train pour nous rejoindre. Donc en toute modestie, je vais partager avec vous quelques mots d'introduction. Tout d'abord pour remercier l'INSA d'organiser cette matinée qui promet d'être riche en informations, qui sera animé par des experts en la matière. Ce sujet du quantique, on en a beaucoup entendu parler, même si on peut encore considérer que c'est un sujet émergent, mais c'est un sujet plein de promesses, plein de gisiers de croissance pour notre société, notre économie de demain. Donc c'est une réelle chance d'organiser cette matinée. Donc je ne vais pas moi rentrer dans des aspects techniques. Je n'ai pas du tout la prétention d'être une spécialiste du quantique. Je m'occupe plus globalement du sujet du numérique aux côtés des services de la région. Je pense que nous avons une réelle chance dans le Grand Est, une chance à saisir tous ensemble. Nous avons des expertises. Nous avons des laboratoires, des universités qui s'y intéressent, une place en or au cœur de l'Europe qui nous revient de faire fructifier. Donc autant de sujets sur lesquels je reviendrai un peu plus en conclusion après les interventions de nos différents experts pour expliquer pourquoi il nous faut bâtir un hub du quantique dans le Grand Est, quelles sont nos chances pour ça et comment la région souhaite être aux côtés de l'ensemble des acteurs pour soutenir cette dynamique. Voilà très simplement en introduction et je vais céder la parole, je crois que c'est à Monsieur Ezratty. C'est ça? Non?
Yes, I will make it
okay.
After that. Thank you, Isabelle.
Okay.
Thank you for your support on this event, and also thank you to be here with us. Yes, of course, to make the resume on that, yes, we need today to have public decision makers, to have the support of companies, but also the researchers to help the government to make a position on this strategy. So now I have the real pleasure to invite near me today the author of many freely distributed books. One of them is Understanding Quantum Technologies. He also published other books like Les usages de l'intelligence artificielle, but also some reports. And he's also, what you don't know about him, he's passionate of photography and also to sustain the woman in digital profession. So please welcome here today Olivier Ezratty.
Hello, good morning.
Let me introduce another special person coming not so far. She's from INSA Strasbourg. She's teaching mathematics and she's PhD in quantum machine learning. So, and also she's passionate about quantum algorithms. So please welcome Kautar Benlamin.
Hello, Kautar. That's your mic.
So Kautar and Olivier will speak with us today about understanding quantum technology, so the book of Olivier, it was published in September 2021. So someone say that understanding quantum technology is a primer for professional, for scientific and engineers, technicians, inventors, and also teachers and students. So I will let you today, Kautar and Olivier, to explain us more in details about your book. Please enjoy.
And the topic itself, not just the book. Yeah.
Hello, everybody. Today we are very pleased to welcome Olivier Ezratty in the Grand Est Region. So for people who don't know Olivier Ezratty is a speaker, teacher, consultant, but above all, he is the author of Understanding Quantum Technologies, the use of artificial intelligence, startup guide, and many other publications. So at the end of this interview, you will know better the person Olivier Ezratty, his book, and also the evolution of quantum science in the last years. Hello, Olivier. So, yes?
I was wondering about the mic, yes.
Okay. Do you hear me well?
Yep.
Okay,
It
that's
should work,
perfect. So before associating your name with quantum science, artificial intelligence, or many other digital technologies, we get interested to the person Ezratty. And we looked for you in the world, and we came across this map. So we find that
why the US? I mean, the name, you mean?
Yeah, we find that you are not only in France, you are also in Scandinavian countries, and you are most located in the American continent.
No, but I mean, it was Ezratty or Olivier Ezratty?
Ezratty.
Okay. It's like a Dupont or... it's not like Dupont, yes. Okay.
So we want to know more about you. Where do you come from, and how did you get interested to quantum technologies?
Okay, where I come from. The name is a Jewish name. It comes from Salonique in Greece. My father was born there, but I was born in France, so I'm French. My mother was French as well. And the reason why you see a lot of green in the US is probably you have a lot of Ezratty in the US. I've got a first degree cousin who lives in New York, so maybe that's an explanation. What was the question, the personal one? Yeah.
It was how did you get interested to quantum technology?
Yeah, how do I got interested in computing? So I'm a software engineer by training. I've been always working in the digital ecosystem, like we say. I was a developer back in the 80s. Then I did some marketing at Microsoft for 15 years. And since 2005, I'm a freelance consultant, like we say. A consultant is the nickname you find when you don't know another name. But I'm doing many, many things under my many hats. And I discovered quantum tech very recently, by the way. Probably I read a lot of stuff on quantum physics when I was young, but I discovered the role of quantum technologies just in 2015. It's recent. Yeah. And you know why? It's when I discovered that D-Wave was starting to collaborate with Google back then. And they had installed the first quantum computer at the Ames Research Center in California, which I visited, by the way, back in 2011. And I saw that D-Wave and Google and NASA were communicating on a giant leap in quantum computing capacity. I was wondering whether it was true or not. And then I discovered that most of the news magazines who were writing about D-Wave probably had no clue about what they were writing on. I mean, and particularly on D-Wave, because D-Wave is even more complicated as a computer to understand than the classical quantum computers we have from IBM and Google right now. It's not a gate-based system, it's a system you program in a very different way. So I was, like on AI, I was saying to myself, when I'm going to be grown up, I was 55 back then, but when I will be grown up, I will understand how it works, discovering how it works. So it took me about a couple of years to understand that.
That's great. And we have seen that you published a book called Understanding Quantum Technologies. So by the way, it's online and for free for people who want to read it.
You can download the PDF for free, like all my books.
Yeah. So we want to know what was the challenge that motivates you to publish that book. And we have seen that you've published many versions. What is the difference between the first version and the last one that you published this year?
The first version was published in 2018. It was my first one. The second in 19, the third in 20, and this is the fourth in English. The three first were in French.
So it was
well, the big difference is probably the fact-checking is better in the recent versions compared to the first ones. So when I reread myself from the first edition, I say, wow, there are so many mistakes, misunderstanding on quantum, particularly on quantum physics. So year after year, I discover this field. I try to translate it in more or less understandable languages, particularly for software engineers or IT people, because I come from this world. I come from a world of, let's say, 500,000 people in France who are software developers, who are IT people, who are developing IT solutions for, everybody, developing websites and stuff like that, startups in that world. And I want to make quantum tech understandable for these people. I know that this book is not for the straw man. I mean, it's not for any audience. You have Julien Bobroff, for example, who publishes very interesting books for more open audiences, even though he doesn't write a lot on quantum tech. He writes more on quantum physics than on quantum computing. So that's it. I wanted to share what I understood. It takes a lot to understand quantum physics and quantum technology. So everything I learn, I share. That's the way I do. I did that in the past for other tech. So that's the way I do.
That's perfect. So we should share our knowledge so that all people can benefit from it.
And you are a teacher, so you know why it's important.
Yeah, that's it. And normally I am a young researcher. I am very interested to quantum technologies. And sometimes I came across a lot of books and I'm a little bit confused to choose that book or that book to read. So what would motivate people to read your book and not others?
Well, first is, I wouldn't say you should read only one book. Probably to write this book, I had to go through maybe tens of books. I looked at all the various ways to teach quantum physics and quantum computing. I was not very satisfied myself by many of the books. And the main specificity of this book is it's kind of the 360-degree view on the topic. So, for example, I start with history. I start with explaining who did what in quantum physics. So between Max Planck, Albert Einstein, Max Born, who's probably underestimated compared to Schrödinger or Heisenberg or Dirac. I learned about the personalities. I learned about the way they discovered quantum physics, and it's not magic. So, for example, when you learn about quantum physics, you learn about, for example, Max Planck, who's the father, let's say the father, and then Niels Bohr, who play a very important role, and sorry, my phone is not in the right mode, so probably it's a sorry. It never happens in conferences like this. Sometimes you think that there's some magic discoverer who discover everything and who has a kind of illumination. No, it was a tough work. I mean, the discovery of quantum physics, particularly between 1900 and let's say 1935, the big years, it was a continuous progress with many people, a lot of arguments, a lot of discussions, passionate discussions, and some of the discussions are still going on. I mean, particularly, for example, what is real in quantum physics? Yeah. It's a big discussion. I know quantum physicists or even quantum foundations philosophers who are still arguing about what's real in quantum physics. So where is the electron, for example, when it's circling around the atom? What is it doing? So is it a wave or is it a particle? This particle wave duality, which is a very complicated thing to understand. So it's complicated. It's still a discussion going on. A lot of people know about the discussion between Niels Bohr and Albert Einstein. It started in 27. It went on in 35, but it's still going on about the so-called non-locality. So it's a passion to get involved there.
So it's true that the quantum field is very tough and it's still uncertain. We don't have answers for a lot of questions, but most of people are fascinated with this field and they want to know more about it, especially students, but they don't have a background. And so what will you recommend students who are willing to learn the quantum science, but they don't have a background?
Well, the selfish way would be go read my book, but that's not the right answer. The right answer is to read many different books, to listen to good scientists, go online, even look at the lessons from Richard Feynman from the 60s. There are many different ways to look at science overall. But it's the same for COVID. Let's take COVID. COVID is not quantum, but if you take COVID, you want to have some understanding of what this virus is. You can't read only one source. You have to read many different sources. You listen to many different scientists. So having an educated opinion on any scientific topic requires having many different sources. But my book lists many sources. So there are, I think I counted, there are about 2,800 different URLs in the book. At the end, there's a bibliography with a lot of different books. For example, the books from Serge Haroche, the books from Claude Cohen-Tanuji are considered as being references, even though if you're not scientist, at page 9 you get lost most of the time. Sometimes you have better books. I recently discovered the notes from Richard Feynman, which are very good to explain quantum physics. There are many different ways to read on quantum physics. So get the pointers and look at the pointers and try to get an educated, not opinion, get educated knowledge about this topic.
That's true that your book includes everything, and what I like the most is there is at the beginning the history, and that we really, it's rarely that we find the history of the quantum. We find it only in an article but not in a book. So I find that it's so interesting. So I encourage students to read your book. And unfortunately, we don't have the quantum computing as a main training in our courses. So most universities hasn't included yet the field of quantum science. Do you think it would be interesting to include it as a main course? And what would be the interest of including such a subject?
Well, it depends on the school, but of course, all schools who are covering computing should cover quantum computing as kind of an elective or whatever, or something that adds to existing classical computing tech. Any school that covers physics should cover quantum physics, of course. But any engineering, I think, any engineering school should cover quantum technologies. That's the reason why I named it quantum technologies, because it's not just quantum computing. For example, another, I would say, covered, under-assessed, and under-taught topic in quantum tech is quantum sensing. Quantum sensing is a huge field. I mean, there are so many things to do with quantum sensing to improve sensing. I mean, measuring whatever, temperature, gravity, or magnetism, anything can be improved with the most recent quantum technologies. So quantum sensing should be learned in many, many different places. Even, any kind of engineering would benefit from understanding what you can do with quantum sensing. Another example is quantum cryptography or quantum telecom. I would argue that's part of computing because telecom is a field of computing some way, but quantum telecom itself is a very interesting field on its own. So the other thing I was willing to cover in the book is showing that mostly everything is quantum. I mean, even existing digital technologies are quantum per se, because
even the classical ones are quantum.
Classical tech is quantum, but it belongs to what Alain Aspect called the first quantum revolution, not the second. What we cover in the book and what we discuss today is quantum computing, quantum sensing, quantum telecom is belonging to the second quantum revolution. So what's the difference between both revolutions? Is the first revolution is about what has been done with the transistor, with the lasers, with GPS, with all the technologies are still rely on quantum physics, but they don't rely on what belongs to the second quantum revolution, which is superposition, entanglement, and also the ability that we acquired relatively recently to control individual quantum objects.
So you would
like
say
one electron, one photon, or one atom at a time. We couldn't do that when the transistor was invented in 1947.
so we could consider that what we have now, it's just like with the things that we have measured in the quantum version. Could we?
What you mean measured?
Because normally when we are in the quantum version, when we measure the thing, we return to the classical one. So
I see. It's we say that also for the way we manage light. We say semi-classical light is when the atom is behaving quantumly, but the light is behaving classically. You have the kind of it's a weird frontier. There's also a frontier that's very interesting in quantum physics is when a particular object is behaving quantumly or classically, and the frontier is not fixed. Initially, the frontier was saying that okay, an electron, a photon, or an atom behaves quantumly, particularly for measurement, or even for the wave-particle duality. But we are discovering now larger and larger objects like molecules which behave as waves and not just as particles. So the classical non-classical frontier is moving over time and over the discoveries we make. But still, it's still in the nanometric field. I mean, it's still very small objects, but the frontier is moving.
okay, so the quantum version is considered like a wave that after we will measure.
Yeah, the good question. Yeah, the right question is what is quantum? What is it to be quantum? Yeah, it's both the fact that at a small scale particles can behave as waves and particles together. The second is quantization of energy levels or different physical properties of objects. Then we have entanglement and superposition, which are the kind of extreme version of being quantum. So there are many ways to define what is it to be quantum. But the basic one is to be quantified. I mean, the quantization of a level of energy. That's what makes it possible to create the so-called qubits in quantum computing. A qubit is just, physically, it's an object that has two levels of energies, for example, and which we can control, but where we can build on top of it a superposition, then we can build a richer way to manage information. That's what it is to be a qubit. But there are many definitions of what is a qubit.
So talking about qubits, we will talk about quantum computer.
Of course, yeah.
So everybody knows that a quantum computer is very powerful as it can solve algorithms in a time much more quicker than the classical version. Are there any advantages apart from speed?
We could have other advantages potentially because all the advantages you just listed it's kind of the advertisement.
Yeah, that's
it is supposed to be the case, but it's not yet true. So There are a lot of people, a lot of scientists, a lot of technology vendors working on making these promises a reality, but we are still far off from those realities. But you're right. What could be the benefit of a quantum computer besides the so-called speed up? I mean, making things faster for some algorithms. I see one very important one, potentially, which would be an energy advantage. So maybe, it's not proven yet, but maybe, given what we know about the quantum physics, maybe we could have some energy advantage with these systems. In some cases, we could have the ability to solve problems which are already solved by classical computing, like let's say in machine learning, for example, but with a better solution, or maybe a more precise solution, or like we say, finding an optimum solution. Existing classical solutions for many existing algorithms use heuristics methods, kind of statistical ways to find a solution. And sometimes it works, but it's not the best solution. So a quantum algorithm, even without the so-called speed up, I mean, providing a much better speed to find a solution, maybe you could find a better solution. It's another way to look at the advantage of quantum computing. So in some places, a better solution is sometimes more interesting than just the speed up. Yeah, so energy, better solution, finding a solution where there's no solution today. So typically, when you want to simulate the way atoms are working together in complex molecules, this is not possible to do with solving the Schrödinger equation on the classical computer. So a quantum computer in the future could solve these equations and find a solution we can't find today. In other cases, it's just being faster. Okay. But faster with an exponential gain. So what is an exponential gain means that you could solve a problem in a human reasonable time that wouldn't be reasonable on a classical computer, meaning more than the age of the universe is not reasonable. I mean, even more than a couple of years is not reasonable. So there are many ways to look at the advantage, the quantum computing advantage.
So quantum computer hasn't only the advantage of speed that everybody advertise. We have a lot of advantages, as you said, solving problems that cannot be solved in the classical version, or having more precise solution, which is really important. So now everybody is fascinated about quantum computer, quantum algorithms, but most of people doesn't know how it really works, what are the challenges of the data transformation. So could you tell us more about this and how quantum algorithms work, and especially...
Well, probably I won't describe everything you list, but there are many challenges to make those promises come true. One of the main challenges is so-called scalability. So today, by the way, that's a big question, a big argument I have with some physicists is the quantum computer real? Does it exist? It's a common question we have. And the answer varies from the interpretation of the question. What is a real quantum computer? Is it a scalable quantum computer that exceeds the capacity of a classical computer, or is it just a quantum computer where you have a couple qubits which interact with each other and where there is some superposition and entanglement and some proof of the concept of quantum computing? So depending on the way you define things, the quantum computer exists or doesn't exist. So if you take the first definition, scalable quantum computer, it doesn't exist, because today there is no quantum computer that's more powerful than a classical computer, so it doesn't exist. But if you take my second definition, which is a proof of concept computer, it exists. I mean, you have IBM with more than 24 systems online today with between 5 and 127 qubits, which are not perfect, which have a lot of errors, like we say, very bad fidelity, but it still exists. You can toy with them, you can program them, you can try your algorithm at a very small scale. It works. You have IonQ and Honeywell, two companies based in the US who have so-called trapped ion systems, which are online as well, with Amazon and Microsoft on their cloud. You have prototype systems working with cold atoms, both in research labs, like here with Shannon Whitlock or Antoine Brouès in Institut d'Optique in Palaiseau. You have their companies called Pascal in Palaiso, you have Quanta, you have QEra, you have Atom Computing in the US with prototypes, not on the cloud, but still it works. So you see, depending on the definition, it exists and not exist simultaneously. So that's quantum as well.
So now with the quantum simulator we have, we only see how the quantum version work, but we don't really see the results that we are looking for, just like precision and speed and all that stuff.
Well, by the way, you have to make sure that the definitions are well crafted. What is a quantum simulator and what is a quantum emulator? There's a big battle around these two words. People don't agree necessarily about what is it. A quantum simulator is a particular type of quantum computing system which solves a problem with a particular design. It's you set a connection between different quantum objects. You define the connections, like if it was a neural network, for example, and you ask a system to find a kind of minimum of energy configuration, and then it gives you the solution, which is the orientation of each of the qubit. Is it 1 or 0 for each of the qubit? And this is the solution of the problem. It's like solving a problem with a neural network. So that's a quantum simulator. It's a quantum system. Then you have a gate-based quantum computer, which is the most common. That's what Google, IBM, and all the players I mentioned are doing. You program a system with a series of quantum operations on 1 or 2 qubits called qubit gates. And then at the end, you read the state of the qubit, and that's the solution of your problem. So that's gate-based quantum computing. And then you have quantum emulation. Quantum emulation or quantum emulator is a way to take a quantum program and to run it on a classical computer. So slowly, with a limitation, which is the memory you have, because simulating the memory of a quantum computing system depends on the number of qubits, and the required memory to do emulation grows exponentially with the number of qubits you want to emulate. So that's why emulation currently works correctly with about, let's say, 50 qubits. You can run that on a supercomputer. Beyond 50 qubits or 55 qubits, depending on the way you emulate, you are limited in what you could do in a classical computer. And let's say you reach 100 qubits. 100 qubits is supposed to be impossible to emulate on a classical computer, because the reason why is you would need 2 power 100 complex numbers storage capacity. So when you exceed, I don't know, 2 power 54, I think you exceed the capacity of the largest supercomputer in the world. But then people argue about that also, because the way you can compress data makes it possible to emulate larger systems. But that's classical computing. That's what you have to know. Yeah.
But they also say that if we have a quantum computer that has only 300 qubits, we can't read the information of the whole world, because 2 power 300, it's like 10 power 90, and the whole information of the world is estimated to 10 power.
That's not true, you know that. Because people are confused between the number of states and the number of objects you have in the universe. So most of the time when what people say, that's what you describe, 2 power 300 is larger than the number of atoms in the universe. Yeah. Okay. But let's say you want to size the number of positions of these atoms in the universe, you would have an even larger scale. So let's compare apples and apples, not apples and oranges. The number of states of a system is not equivalent to the number of objects of another system. So that's why the comparison doesn't make any sense. That's my view. I don't know if physicists agree, but it doesn't make sense to make this kind of comparison. But still, the number of possible states of 2 power n qubit system is huge when n grows, of course. Yeah. That's, by the way, what makes some physicists skeptics about the capacity to run this kind of system, because they say it's too many states, so maybe it's not possible. So that's one of the reasons of the skepticism. It's too many states in one simple computer, so it drives skepticism.
So now everybody is talking only about the advantages of quantum computer, but we don't cite the limitation of it. So what are the limitations of a quantum computer, and when do you think we will have a real quantum computer?
Famous real one, yeah.
The famous
Well, the
question.
limitations, it depends if we speak about the limitations of the future scalable quantum computer, or if it's the limitation of existing quantum computer. Both may have limitations,
we would say
but
both.
different limitations. The limitations we have today are that we can't scale the number of qubits of a quantum computer because of a physical phenomenon called decoherence. Decoherence kills superposition and entanglement to make things short, and it kills the capacity to compute on a computer, on a quantum computer, and it kills it very quickly. If you take, for example, the example of superconducting qubit from Google and IBM, the stability of the qubit doesn't exceed 100 microseconds. So it's a very short time frame. And during those 100 microseconds, you can run a series of operations which are called gates. And the length of these gates, depending on the technology, is between 20 nanoseconds and 600 nanoseconds. So it means that theoretically, you can't run more than a couple hundred series of operations. But there is another problem. That's decoherence. Decoherence is something that kills the quantum state of the qubits. But before decoherence, you have noise. And the noise is a source of, it's called also from decoherence, but it's a progressive source of error that destroys slowly but surely the state of the qubit.
And the noise comes from the noise of the construction of the qubit, or the noise on the...
The noise comes from decoherence, but it's the interaction between the qubit and its environment and other sources. It depends on the type of qubit, by the way, but you have a lot of different sources of noise. And what you have to understand is the noise creates errors in computing, and the errors we have right now in quantum computing are huge. I mean, if you take the classical existing quantum computers right now, we have an error level that's between a tenth of a percent to a couple percent for gate operations and also for reading the result. And if you do many operations one after the other, you add the errors, or you multiply it, by the way. So you add the errors. So let's say you have a 0.5% error rate. If you do 10 operations, you will have a huge error rate in your computing. And it's exploding. So one of the solutions that is being envisioned by quantum computer physicists and designers is to implement so-called quantum error correction system. So you correct the errors. And what you have to understand is the way people plan to correct the errors and compare it to classical computing. If you know classical computing, you know that you still have some errors. For example, when you send 1 byte of information on a telecom line, there is an existing error correction system. It's called parity bit. So you add another bit that you can use to correct some errors happening in telecom lines. In quantum computing, the overhead of error correction is huge. I mean, the best of the technologies being designed right now adds 30 qubit per qubit to correct an error. And superconducting qubits are said to require at least 1,000 qubits to correct 1 qubit. So it means that, and the term they use, and it's described in the book, is a logical qubit. A logical qubit is a system comprising many, many different physical qubits, which from the developer view is corrected with a minimum error rate. So the overhead is huge. And what slows down the progress of these systems is to make sure that we can build many, many, many qubits, many physical qubits with a reasonable error rate to assemble them in a logical qubit. But the problem is, how do you scale these systems? How do you scale from the energy standpoint? How do you scale it from the cabling standpoint in some cases? How do you scale it from the thermodynamic standpoint? For example, if you need to cool the qubits like we do with superconducting qubits or even electron spin qubits, you have to cool the system. You cool it at 15 millikelvin for superconducting. You cool it to 100 millikelvin to 1 Kelvin for electron spin qubit. And the cooling power is limited. And then you need to have a lot of electronics controlling all of that, and that doesn't scale very well right now. So there are a lot of engineering problems to solve. What's interesting is those engineering problems to be solved are not just quantum. Some are quantum. I mean, reducing the noise is a quantum problem, but making sure that classical electronics work at low temperature, making sure that you have more simple cabling, making sure you can multiplex information in and out of the system. These are more classical electronics problems. So it means that the scope of engineering problems that have to be solved will be addressed by many different kinds of engineers. And that's why there are many different ways to become a quantum system engineer. Some will be really quantum physics specialists, but some will be, I would say, more classical electronics engineers or more classical RF design, for example, radio frequency systems engineers. You have to craft precise waveforms of radio frequencies, microwaves. So this is classical electronics. So we need this kind of engineering skills, and that's why in schools like INSA, it's very important to learn all the technologies that are required to create a computer, and not just quantum physics. Quantum physics is a big part, of course, but around quantum physics, you have a lot of other engineering, electronics, and physics to learn.
What should be done to achieve scalability?
Cryoelectronics, cryogeny, reducing the noise of the system, but it depends also on the way you control the systems. If you take the cold atoms, which are being worked out by Shannon Whitlock here in UNISTRA, it's a different way to control the quantum objects than superconducting, electron spin. Everybody has a different system. And everybody has his pros and cons. I mean, everybody has advantages and disadvantages. So problems are different from one type of qubit to the other type of qubit. Maybe we'll discuss that in the panel. So the problems to address are different. Then you have algorithms. You mentioned that.
Yeah.
So the problems you have to address in algorithms is making sure the algorithms are optimum, that they require a minimum number of qubits and a minimum number of qubit gates. So kind of resource-dependent aspects have to be worked out in designing the algorithm. There's a huge challenge in creating quantum algorithms when it deals with feeding the system with data. Feeding, for example, the field you work on, I mean, quantum machine learning requires a lot of data, and feeding a quantum system with data is probably one of the biggest challenges we have right now, because we lack a technology that's called quantum memory. Doesn't exist yet. We would need that for many algorithms. If we don't have that technology, we have to find more efficient ways to feed the quantum computer with a significant amount of data, or you have to compress classically the data before it's put in the quantum computer. So it's a mix of various disciplines in classical engineering and quantum engineering that's required to build that. And what I believe for the new discipline that is quantum computing, I believe that we will need to have a more diverse, I would say, workplace of engineers with people who know about algorithms, people who know about complexity theories, mathematics, classical electronics, quantum physics, and people will have to discuss with the other. What I've discovered when writing the book is there was not enough, I would say, pluridisciplinarity or transversality between those engineers. People are isolated in their silos, and we need to have more discussions between those people. For example, when you build an algorithm, you should have a full stack view of the algorithm. So understand what's in all the stacks, understand where the speed up is, compute the speed up with all the aspects of computing. For example, quantum error correction is most of the time not built in the way to assess the speed up of an algorithm. So I would say, why is that? People should have a more global view of how the computing system is built to make sure that they know about the real benefit it will bring full stack.
So to achieve scalability, we should cover a lot of fields. And what is much more important is that everybody should share information between them, so we can go faster. Sometimes we are looking only in our field, but if we discuss with others, we could find the solution in.
That's probably why there is some innovation to create in the way we teach these disciplines in engineering schools. Probably we may have to revisit the ways we do that. I'm not sure it's maybe that different from classical computing, because we have already those silos. I know that most of the people who do software development, they have no idea on how a microprocessor is being designed, is manufactured, or even works. People even don't know what's firmware, how low-level hardware works. People have no idea of that. In quantum computing, maybe it will be the exact same story in 20 years, but in between, I think quantum software designer will need to know more about hardware. They will need to know about the limitations of hardware or the ways to expand the hardware capacity, memory, like I mentioned. There are many, many different aspects that should be learned by quantum engineers. And so I'm pushing for more inter or pluridisciplinarity in the way we teach quantum technologies than what we do today in classical computing. That's what I would push. But it's a personal view, that's all.
I have a question concerning right now we have a lot of applications in the quantum field.
We didn't talk a lot about it.
So if you have the opportunity to contribute in a specific application, what would be in a specific field? What would be that field that you will?
You mean me or the industry overall?
No, you.
Oh, me. I'm not sure I could contribute directly, but when you look at the potential applications of quantum computing, it's very diverse, and on top of that, still, it won't solve any problem. A quantum computer is not just a faster Netflix server or faster email server. It's a system that will help solve specific mathematical problems that are not solved right now in a classical simulation on a classical supercomputer. So it's at the beginning, it's going to be a narrow field of what we can't do today or can't do efficiently on a classical computer. It's not all the digital technologies we are using. It won't replace your smartphone, it won't replace your laptop, it won't replace 99% of the stuff you do on your laptop. So that's first thing to understand. The second is when you look at the field of application, it's very diverse, and I would say that from the human, from the mankind future perspective, there are kind of highly positive outcome solution and classical business-oriented outcomes. Let me give you the example. The first category boils down to chemical simulation, biochemical simulation, and everything that's linked to the environment and energy. So quantum computer as a promise could help scientists solve some of the problems we are facing right now with the climate change and with healthcare problems. So that's very positive outcome, potentially. So how do we reduce the energy spent to produce some materials that could be interesting from the for mankind. The second category is more how do you optimize your way of life, like transportation, marketing, finance. I would say it's more classical. It won't change the world. I mean, for example, there's one application of quantum computing. It's optimize a financial portfolio. Nice. It's nice. Okay, you can minimize your risk or optimize your return on investment. But let's say quantum computing becomes commonplace. It becomes mainstream. If everybody is using the same algorithm, it will level the playing field. So it won't create a huge benefit for everybody, because everybody will have the same algorithm. You see what I mean? So it's not that a big change. And then there's the last one, that is one of the big motivations behind governments putting a lot of billions of dollars behind quantum computing is solving the so-called Shor algorithm. It's a way to break the cybersecurity of the existing internet. So this is far from being feasible. I mean, to break the internet today, you would require at least, given the existing technology, 20 million functional qubits. When right now, it's even difficult to have, let's say, 20 to 50. So, Okay, maybe someday it will happen, but it's a huge technology challenge. I wouldn't say that is a positive outcome. So breaking the internet is not a positive outcome. It's a destructive outcome. It will probably cost a lot of money to build those systems. It probably cost a lot of energy to break the internet. So I don't think it's a positive outcome. So, but hopefully, from the historical standpoint, what I see in the way the technology is going to mature is, I say it's the reverse atomic bomb story. It's kind of bizarre as a story, but you know about the atomic bomb. It was created in the 40s during World War II. It was a huge investment from the US because they had a fear that the Germans were building the same weapon. So then we have again Nagasaki and Hiroshima, the other way around. And then you had civil nuclear that we have today in France, which produce 75% of our energy, electrical energy. So the weapon arrived before the civil use case. In the case of quantum computing, it will be the other way around. Because when you look at the capacity that is needed to solve some of the chemical simulation problems I mentioned, some of the healthcare problems I mentioned, some of the classical energy optimization problems I mentioned, those things will probably be possible way before we break the internet with Shor algorithm and the 20 million qubits, you see? So it means that the kind of military or intelligence negative outcome of quantum computing, if it happens, will happen much later than the positive outcome of the technology. So that's the way around. It's completely the other way around compared to the history of the atom. I don't know if it's it's enough to making people secure about it, but it's a different view about history and the way progress shows up.
So every technology has its drawbacks and
Exactly. And it's the responsibility of scientists, of entrepreneurs, of users, like enterprise users, to make sure that the positive usage are prioritized on top of the, I would say, the negative or the some of the usages which have some drawbacks. So, but you know, if there's a hunt for profit, people will use what is profitable. So you never know what happens. But the responsibility of scientists is also to orient a little bit the way research is being pursued to favor the positive usage of technology. It's a big responsibility. The same for energy. I mean, I'm working with a friend in Grenoble, Alexia Ofev, to make sure that we have now scientists thinking about the cost, the energetic cost of quantum computing, to make sure that right now it's being designed to save energy, not to be a big energy spender like we have today with AI, for example, or with all the data centers which are energies hungry, too hungry right now.
What are the societal and environmental impacts of the quantum science?
Globally?
Yeah.
The societal impact, it's a good question, yeah. There are many. Right now, the thing is, how do you make quantum tech being understandable by the greatest number of people? It's a challenge. I mean, it's already a challenge to teach that to engineers, or imagine your mother-in-law or your grandmother, your kids. So there's a kind of skills challenge to make sure that people understand what are the stakes of these technologies. Even though any user of a smartphone have no idea about what are electromagnetic waves. Nobody knows what's, 3G. You know that 5G is faster than 4G, but you have no idea about how it works in most of that. Nobody has an idea about how a microprocessor works within a smartphone, or memory, or even an LCD or OLED screen. Nobody knows that. But still we think that it would be useful to have some understanding about how the technology works. The second is the use case. We mentioned that already. That's a huge societal impact. And some good lessons can be driven out of the recent experience we have with AI. You probably remember Cédric Villani published a report back in March 18, and then there was a big wave in France and also in Canada and the rest of the world to create so-called ethical AI. People were thinking about how can we build an ethical AI system, how can we avoid bias from AI, particularly in machine learning, because the data drives the creation of biases, and that's a problem. So AI drove a big wave of people thinking about the ethics of this technology. But you know, it could have been thought out way earlier. We could have thought out of all those biases and all those problems with data even before AI, because it existed before. I mean, most of the problems we have with AI right now existed before AI, or before the current wave of AI. It existed when microcomputing started, when the internet started back in '95, big data started in 2000. Those problems were already existing. So what can be done with quantum technologies is to think about those potential problems early on, to have a discussion, to provoke the discussion between philosophers, engineers, scientists, entrepreneurs, users, I mean users being companies, to make sure that this discussion is being launched early on to avoid being trapped later in the adoption cycle of the technology in a kind of lock-in scenario where people think like an obsession about, we will have ethical quantum. So you see, it's kind of preemptive strike, I would say. The industry would benefit from having a preemptive appropriation of those ethical and societal questions before it happens too late.
And do you think that we are in the right road right now? There are a lot of startups that are working on. So is it enough, or should we invest more in
regards to societal issues or overall?
Overall.
Well, you know how many startups we have right now in quantum computing? It's not a lot. I mean, there are many different data. Michel Kurek was there and knows that there are many ways to count the number of companies in quantum tech. It's between 500 and a couple more hundreds, maybe 500 to 700. It's not a lot. I mean, if you compare that to the number of startups in blockchain or AI or whatever other digital technology, it's not so much. Even what you take the amount, recently we've heard about crazy amounts that were raised by a couple companies like IonQ, PsiQuantum in the US. So those two companies raised more than $600 million. I see your eyes, Alina. It's a lot of money. It's just pocket money. I mean, when you look at what happens, I look at the data, for example, just in Q2 this year, all the blockchain companies raised more than $15 billion worldwide. And so the total quantum computing startups live to date, so meaning since it started, it's less than 4 billion. So given the positive outcome, the potential positive outcome of quantum tech compared to the amount that was raised, it's just pocket money. I mean, all the startups in the world this year, they will raise more than $300 billion worldwide. $300 billion. And quantum computing, quantum tech, it's less than 4 billion live to date. So you see, when you look at the scale, it's always important to have an idea of the scale. It's nothing. It's just nothing. So I wouldn't worry about the amount of money that was put in those startups. I would be worried about something else, which is the difference of money that was put in European startups compared to North American startups. I did the computing myself, so the data is in the book at the end of volume 2. Europe overall has the same number of companies in quantum tech than North America, meaning Canada and the US. Same number of companies. But the US accounts for more than 80-something, 83, I think, or 86% of the amount raised, and Europe is about 6% of the money. Same number of companies. That's the problem. It's not the 4 billion. The problem is Europe, how it can be defragmented, how can we have larger companies, how can we have more money in the best of the startups we have in France. For example, in France, we have about, let's say, 20 startups, and the largest fundraising were recent from Pascal. It's a cold atom company, cold atom computing system company, and Candela, which announced just in November. So it was 25 million euros for Pascal and 15 million euros for Candela. It's good. It's the beginning. But we are comparing these companies with companies who raise between 70 and 700 million bucks in the US. So that's one of the challenges we have right now.
So I hope that in the future will be better.
Yeah, it's beyond the discussion here. Maybe we should take some questions from the audience, no?
Yeah, we are at the end of our interview. I have only the last question. If you have something to add to your book or to the person Olivier Ezratty, what would be that thing?
What I loved, what I would love with the book, it's the first time I publish a book in English. All the other books, I published 46 books before this one. They were all in French. And what I wish was that this book would help the French ecosystem and even the European ecosystem to some extent to be more visible worldwide. I want to showcase also the work of the scientists we have in France, particularly. It's not a way to rewrite history, but when you read quantum physics history viewed from the American standpoint, the French are nearly invisible. It's so amazing. So we need to raise the awareness of what the French and Europeans have been creating here. We are very good scientists. We are very good entrepreneurs as well. I wish to be a small contributor to making things more visible. And it's tough. I mean, it's tough. We have a lot of competition, even in writing. We have a lot of competition online, so it's tedious work to make sure that we are visible. I want scientists to be more visible. I want scientists to talk more in the media. I want more Étienne Klein, for example, in France, more people who are able to talk to a wide audience public. I would like to have more French scientists being visible at an international scale. When I mean French, it's not just French by nationality. It's French meaning working in a French lab, for example, because we have so many researchers in France who are not French, like Shannon or Yordanis Karinidis or Eleni Diamanti, who are Greek, Eilham Kashefi, who is Iranian, but she's got a British passport, Zaki Lektas, who is a co-inventor of the so-called 4 qubits, is a British passport, and he works in INRIA with Maziar Miraimi, who is Iranian. So we are a country that welcomes the best talent from the world, and we still need to attract the best talent from the world. So it's researchers in France more than French researchers.
Thank you very much, Olivier. Thank you, Kautar, for this overview on your book. And I think we have a lot of questions to continue, but we have the chance to have you here today with us, and this is already a good point. I would like to know if someone has some questions and it would like to ask to Olivier.
Shannon?
Yes.
Thank you very much. So one of the remarkable things about your book, I think, is that you published it fully open, right? So I was hoping you could comment a little bit on the importance, or from your perspective, of open science and maybe open knowledge sharing for developing this technology, and especially considering, let's say, the divide between academia and the private sector.
Excellent question, yeah. Since I can explain why I publish things like this. You know, before I was a freelance consultant, I worked for a company called Microsoft. And back then, I mean, back in the early 2000 years, it was the archetype of the proprietary company, proprietary software company, not open source. And I wanted to create a kind of a paradigm shift with leaving the company. So that's why I call my blog Opinion Libre, free opinion, saying now I'm free. And then I decided to publish everything in open source. So you see, that's one of the explanations. And then, of course, I believe in open transmission of knowledge. But still, when you move to the private sector, I mean, you become a vendor, you have to protect your IP, you have to have patents, and it's a different world. So we need both. I mean, we need a world of open knowledge sharing, particularly when it deals with students. One of the reasons all my book were open source was one of my audience was students. I mean, students, whatever they were doing. I mean, students in business schools creating a startup, because I published a startup guide for 15 years. Students in AI, so more in the science field. Now students in quantum, whatever. I use a marketing trick, which I can disclose for you. The marketing trick is the following. In the world, right now, you have people who have money but no time, and people who have no time and the other way around. So I'm confused there. So time and money, and no time, and time and no money. See what I mean? So a student have a lot of time but no money. A business decision maker, he has not a lot of time but he has money. So the business trick I use is I sell the short version of the book to people who have no time and money. And those who have time but no money, they get the book for free. So that's the trick. It's a universal trick because it works everywhere. I mean, if you want to study on your own, you could do what I did, is look at 2,700 books or research papers and read it by your own, and then build your knowledge out of it. So I am an intermediate in that stage. So of course I believe in sharing the data. And what's interesting is I couldn't have written that book probably 15 years ago. Because 15 years ago, archive was not as popular as it is today. Open source research content was not as open as it is today. And now I can write this kind of book because probably 98 or 99% of the research material I want to access to get information or get data is open. It was not open 20 years ago. So the world of research has changed for the better, for that respect, and the book is the result of that change. So of course, I'm favoring that. But when you move in the business sector, things are changing. You still need to behave differently. And that's the difference between science and technology. When you create technology, you have to protect your technology. You have a lot of competition. It's a business competition. It's not just science competition. And then you have to behave differently. So I wouldn't advise to publish a book like this on how PsyQuantum works. Of course, how such a technology from a techno vendor works. What I would like to do on my own is to get information and publish it. But it won't come from the vendor. See what I mean? So I don't know if I answered well your remark and question. That's my thought about it. Yeah. Madame.
Thank you. It's a really interesting topic. And one of your subtitle I read about quantum fake science. Is that contributing or manipulating technologies?
So you saw the quantum fake science part in the book, yeah?
Yes, but unfortunately I just had the volume.
Oh, it's a volume 2,
it's
yeah. You can get it online. So yeah, I started to dig into that topic 3 years ago. And surprisingly, there's no book writings on this. And I hate fake science. I hate, when I mean I hate, it's not just a passion, but I want to correct things when it is possible. And I saw that there are a lot of people, and it started a long time ago, it has started more than 10 years ago, who are manipulating weak people with using the quantum nickname for fake medicine particularly. And there are many, many fake medicine sciences being promoted. Sometimes it's mixed with other mixture that I won't describe here because it's very political. And I find it a bit dangerous. It's like a bit like anti-vax around the COVID. So this is the same kind of phenomenon. So, and so I felt it was interesting to understand where those fake science were coming from, what were the intellectual process that drove people to sometimes use real science and to manipulate it to create a fake science or fake technology or fake product. And it's very interesting because sometimes when you start to, let's say, take Roger Penrose, for example. Roger Penrose, he just got a Nobel Prize last year, but he's known for a theory about how the mind works in the brain. It's based on a very low-level understanding of how the neurons are working with some quantum effects. And then he explains that this is conscience in your brain. So he makes what we call in science reductionism. So he takes a very small item explaining a larger macro item in the way conscience works in your brain. And so I try to understand that. Same for water memory from Luc Montagnier, etc. So I try to understand why are we having this and how is it happening. So there are about, I don't know, 25, 30 pages in my book on this because I found it interesting. And then I chose another approach, which was humor. And one of the best parts of my book in volume 2 is quantum management. Because it's a fake science. Because I discovered companies who are really selling quantum management consulting services. It exists. And then I said, I'm going to do my own. So I did write just 4 pages of fake quantum management science. And I'm embedding in that all the stuff I can find from quantum computing or quantum physics, just to make fun of the people who are using analogies to build a fake science. Quantum marketing exists as well. I participated to an event last week on that. It was so funny. But so and there are people who are selling quantum marketing or quantum advertising, saying, "Oh, what the heck? Stop doing this." So, well, but you know, it's like it's crazy to do that. Well, you know, I don't know if you know this picture of somebody. It's a very old cartoon. There's a guy. He's on his PC at home. And his wife is waiting for him, saying, "What are you doing?" Saying, somebody is wrong on the internet. So he's typing to make an answer. So it's like boiling the ocean. You can't address all these fake science. But still, I've got a small part on my book, and I try to address it. Did it answer your question? Yeah? Okay. Daniel? No? Yep, there's one here. Here? Yeah.
Hi, good morning. Thank you very much for this. My question is about money. And
about what?
Money.
Money, okay.
Yeah, you said there is a huge difference in funding between the US and Europe. What I would like to know if this is the difference of public power in this. Are the Americans, is the US government funding more compared to European countries? And can we really compare US and Europe, knowing that French government has its own strategy, German government has its own strategy, UK, Netherlands, and from a European perspective, do we have a strategy, and can we really compare the two continents?
Well, there was a video from Neil who was missing, but well, if you compare the amount of money that goes in public research, of course the US are well funded. Federal research, both in the civil and the military intelligence side, are feeding a lot of research organizations. But when you look at the quantum plans that were designed by the US, by EU countries, by the UK, and China, Europe is not that bad. I mean, when you make the total of all the plans in Europe, it's more than 5 billion euros or dollars across 5 years. The US officially announced a plan of 2 billion, but it was on top of an existing legacy of investments that was significant, but not evaluated, by the way. There's no number about the existing investment. France is 1 billion euro public funding plan. Germany is 2 billion, including private money. UK spent about 1.2 billion pounds in 10 years, life to date. China announced various numbers, but the real number for China is between 2 and 3 billion euros in 10 years, so it's not that big. The big difference between the US and Europe is not public funding. It's really venture money. Because most of the money coming to startups went to US startups through US investment funds, because there's a lot of money in the US and it goes in priority to US companies. And one of the big goals and challenges we have in Europe is to make sure we can attract American money or even some kind of Middle East money in some cases, because that's where the money is. It comes from either the US, Wall Street, pension funds, or oil, most of the time. And we should be able to capture some of this money and to make sure that our startups become international as fast as possible. They address the American market very quick, because the US market, whatever you think about it, is a defining place for creating standards. The American IT market is about 34% of the worldwide IT market. Europe is smaller. Europe has a GDP which is a bit bigger than the US, but we spend less money per GDP euro in innovation and in digital tools than the US. So it creates a big difference, and so the US market is still the defining market. And Europe has a big weakness which can't be solved, which is it's a fragmented market. Different languages, different cultures, even antitrust regulations which prevents the creation of European-wide telecom or whatever big company it could be. So we have a big weakness, which is we are not an homogeneous continent compared to the US, and that's why we have to play judo and try to leverage the strengths of the US to create worldwide companies and not just try to play in our own field. Daniel? He's working for an American company, so probably he's got some advice on that.
Yes, thank you. You know, Olivier, you and me, we come from a time where we started in the business, the technology, when there were computers and software. Now we are talking quantum technologies, we are talking quantum computing, and I assume that quantum computing is like, you know, the previous computing, which there will be machines and software.
Yes, you're right.
Okay. So what is going to be, most probably, very importantly, what will be the standard in terms of machine? Do we have a chance as Europeans to develop the quantum computing machine, or is that a battle which is lost? And is that the most important thing? Where is the big differentiator? Where is the big advantage? Should we be developing the machine or the software?
Question. Short answer would be, one is we don't know yet which of the quantum technology will scale better. Today, you would be a real good forecaster if you would say it's cold atoms, trapped ions, that those are the technologies that are being used to create qubits or superconducting qubits. There are about 6 to 7 classes of qubits, but within the classes there are subclasses. So it's like if you had very different kinds of transistors to create a chipset for a classical computer. There's a big diversity. This diversity is interesting because the challenges are so high to build a scalable computer that it's good that we have different paths around. Because if we had only one, we wouldn't have any fault tolerance. We need to have fault tolerance in the way we do research. We need to have different technologies. So you don't know yet. What I would say is I don't believe in a situation when only one technology succeeds and all the others fail. And there is one reason for that, which is if you want to build a complete quantum computer architecture, you will need about 3 key technologies. One is for computing, one is for memory, and one is for communication. And it happens that the technologies that are the best suitable for these 3 things are not exactly the same. For example, for telecommunication, you need photons. You need light because it travels at long distance. No other technologies, at least quantum-based, travels long distances like photons. Quantum memory, it's better with cold atoms and a technology called NV centers, which is not necessarily the one which will succeed in computing. And in computing, it may be some other. So you will need to assemble different kinds of technologies to make a whole system work. So that's why you need to invest in many different technologies simultaneously. Then you have the question on software. That's another huge battle. The battle has already begun. You already have so-called software frameworks, which are becoming very popular. And one of the most popular framework comes from IBM. And even if IBM is not succeeding in building its own scalable computer in the one single technology they have chosen so far, called superconducting qubit, they have already nearly won the battle of the software framework, like TensorFlow for AI. So they have a system called Qiskit, and Qiskit is already the most used in the world. And they are being competing with similar toolkits from Microsoft, from Google, from all the vendors, even D-Wave. They all have their own frameworks, but Qiskit has been pushed for 5 years now by IBM, and it's one of the strengths they have. And so what I believe in, at some point, when the technology will mature, you will have very few software development toolkits that are successful, like for AI today with PyTorch and TensorFlow, for example, and scikit-learn, to take the 3 most popular right now. And you will have a small number of toolkits covering different hardware architectures. That's what probably will happen. And so the battle has started 5 years ago. We are already losing it right now. Nobody thinks a lot about it. I don't hear a lot of discussion about it. And it's a big question to be asked. And I have some ideas which I won't share here to how do we counter that. So there are some ways to do it.
A last question.
There was one here. I didn't say it? Okay. And you know we have 2 panels now, so there's going to be more discussion in the panels. Yeah.
I guess you already answered the question, but so there are many techs implementing qubits today. My question would be, would you be able to make a little bit of a commitment in saying which one you believe is getting more traction, which one is waning, or can you give us a little bit of an insight into what is popular today? What is getting popular?
There's a difference between those 2 things.
Sure,
what is popular and what has the more potential.
Yeah.
Could we leave that for the panel? Because we have a panel on qubits, no? It's the topic of the next panel, so
okay, sure.
We will have a discussion with the other panelists on this question. I think I would just suggest. I have got some ideas, of course, but others as well.
Yeah, so we will thank you very much to the public for the questions. Thank you, Olivier and Kaotar. And just let's some applause for
Thanks.
them. Thank you. And stay with us after the break, because we are going to speak about qubit platforms and quantum computing for the first roundtable, and then we are going to speak about teaching and innovation ecosystem in quantum. So stay with us. We have.
I have one request for you,
break.
please.
Yes.
Open source means contribution. So it means that as a reader, provide me any feedback you want. Spelling, typos, there are many in the book still, but the last version is online. This one is an old one. Because the time it takes to print it, in between I publish about 3 different versions. So I did correct a lot of typos in the version online, but still any recommendation you have, any information source, any way to improve some explanations, I take it, I share it, I give credit. So anybody can contribute to improve that book. I already have tens of people who contributed to this. So don't be shy. Send feedback. Thank you.
Thank you. Thank you again.
démarre rapidement et reste rapide dans le temps. Car plus vite vous vous mettez au travail, plus vous aurez de temps libre pour le reste. Ah oui, ça va vite là quand même. Choisissez la rapidité. Choisissez Chromebook.
go forward with our event today. So I introduce you Pierre Grussenmeyer, and I welcome him to the scene. He is the director of INSA Strasbourg for the research department. So I will let him to say some words about this opportunity to have Olivier Ezratty and other experts in quantum and here today with us to INSA Strasbourg.
Yes, just a few words to welcome you physically at INSA, because I think it's not simple to do that, but we did it today, and I'm very happy about that. I'm not at all a specialist in quantum technology, but I'm very interested, of course, because we have to think about the future for our teaching teams, for the students. So that's we know that quantum technology is getting more and more popular and concern the entire scientific community, whatever the domains, and we have engineering fields and architecture at INSA, and I think all of them will be concerned in the future. I think for INSA, one of the main objectives is to develop a broad knowledge of quantum science, and you already talked about this morning, and its application among the whole community, for both teacher and students, as I said, and also for the socio-economic partners. We have many partners at INSA, and as we did it for the AI in the 3, 4, 5 last year, I think we have to think about that for the quantum technology in the community. Only a few and sometimes very complex lectures on quantum technology are currently available, and we have to work on how teaching and communicating about the topic. It's very nice to have the books, and I'm sure those who are here will enjoy reading the books, and of course I understood that the documents are online and will evolve from months to months. We believe that designing quantum engineering training accessible to all specialties in engineering science, including issues of inclusive and equity, is a challenge for the coming months. So I'm also happy today to have several academic partners, ecosystem players, and local and regional authorities here, as well as private partners. And I thank you for being here. And I think it's very important to think about the creation of what Alina called the so-called quantum hub for the Grand Est region, and I think Mrs. Kuhn will also say a few words about that. Thanks to Olivier Ezratty, I think you are doing a great work, and it's a pleasure to listen to your presentations. There are many fields: quantum physics, quantum computing engineering, quantum computing hardware, quantum enabling technologies. You said you discuss about that later. So that shows that the domain is huge. So it was my pleasure to listen to you for the first hour. I was a bit late for some technical reasons, but nothing important. I would also like to thank the different speakers who have accepted to participate. Thanks to Shannon from the university, with whom we are organizing the event. Thanks to the colleagues who accepted to be part of the roundtables. To Mrs. Kuhn from Grand Est for being here, to Jonathan and Michel from the Feynman Foundation. and to the Pascal startup represented by Mrs. Kaima Bouaza. Last but not least, I would like to thank Alina. I think you know that Alina is pushing forward on the topic, and also Stephanie from the INSA research office, because they did a lot in a very short time to make this day possible. So thank you very much to them, and I wish you a nice day in Strasbourg. Enjoy the Christmas market. It's a good time for that. Thank you.
Thank you, Pierre. Thank you very much. So we are going to go forward right now, and I would like to invite to my side Ines George, which is a PhD. It's a graduate student in electrical engineering from INSA Strasbourg. She also won the first prize in the final of Great Est Region for my thesis in 180 seconds. So congratulations again. And she's having she was having a presentation on her subject thesis, which is the predictive maintenance of lithium batteries in electric vehicles. So thank you, Ines, being here with us today. And together we are going to present, to invite the person who are going to be part of the first roundtable. So Ines, I will let you the floor.
Yeah, well, first of all, thank you for having me here. It's a real pleasure to moderate this panel. And I would like to welcome Shannon Whitlock on stage with us for this first panel. Shannon Whitlock is a professor at the University of Strasbourg. He's teaching experimental quantum physics, and he's the coordinator of the Access, which stands for Atomic Quantum Computing as a Service. So welcome here on stage.
Okay, we are continue with Jonathan Attia, the chairman of Feynman Foundation, and he is also the working group chair for the Quantum Algorithm Design and Development E3I, and also Quantum Computer Architecture Working Group for E3I. So welcome, Jonathan.
Okay, well, we welcome on stage also Olivier Ezratty. You already heard him. No need to present him further, but he's a famous. Thank you for being here again.
Yes, and also Kautar. Welcome, Kautar, again to the scene, near to Olivier, of course, to support. Yes, and we have also Shaima Bouaza, which is the business developer of Pascal. I don't know if she's still with us. We are trying to reach her on GoToMeeting. So she's going to reach us. Meantime, we are going to start. So I will let the floor to Ines and to moderate this roundtable, and I hope you will enjoy. And we keep in touch because you are going to have some questions maybe for them. So don't be shy.
Should I keep the microphone?
Yes.
Okay, so welcome everyone on stage, and without further ado, let's start the discussion about quantum. Sorry. I'm really sorry. Okay, so let's start the discussion about qubit platforms and quantum computers. I'm very sorry for. Well, Olivier, you talked earlier about your book, and you talked about what is a qubit. You already gave a definition of what is a qubit. Yeah, quickly. I know it's hard to give a definition, but I wanted to ask you something else about those qubits. I mean, there is a lot of agitation about this subject, about the qubits, but why? How can you explain that there is such an agitation about this subject, and how can you explain that there are so many actors in the field? And well, what do you think about it? Why such a hype about this subject?
It's not agitation around the qubits. It's more about quantum computing globally. Yeah, that's the sense of your question. the agitation started back in '94 with Peter Shor algorithm. It created a lot of excitement with governments who thought that quantum computing would be a kind of new weapon, not a nuclear one, but a weapon to control cyber security. So it drove a lot of excitement with government. Then there was a lot of creativity in algorithms showing that quantum computing could bring huge power to do chemical simulation, optimization, whatever. And so it drove another kind of excitement that was more a civil one, not, I would say, intelligence or military driven. So that's probably an excitation. The other thing which happens right now, particularly in the startup scene, is the so-called FOMO phenomenon. You know, FOMO, it is fear of missing out. It's kind of, when you have a new technology showing up, it can be anything, metaverse right now, it can be whatever, blockchain or other tech trend. There's a huge fear from large investors to miss something and to miss the next Facebook or the next Apple. So investors are ready to put money in even weird technology that could be a potential big winner in tech. But I can give you a number which I quoted in a paper I'm going to publish. It's not in the book right now. In virtual reality, there's a company called Magic Leap. Magic Leap is creating augmented reality lenses. It's competing with Microsoft HoloLens. That company alone raised about $2.6 billion, which is nearly all quantum startups altogether, nearly in a kind of scale. So it's an example, and this company is failing right now. So it just shows that there is money for new ventures, new fields, new exploratory fields, and quantum technologies is one of those fields, and it makes sense why there is those crazy amounts with PsiQuantum, IonQ, Rigetti, and others. That's it. Then there is the magic of science, I would say. The quantum science has a lot of mystics around it. All the scientists from the 20th century are very known about it. It's got a kind of magic sauce to change the world. So people think about this potential to change the world. It's a mix of explanation. It's all of that together, I would say.
Yeah, everybody wants its share of the
Exactly.
progress. Yeah, I can understand. Well, around this table we have a great diversity of actors in the field of quantum computing. And well, I wanted to ask you, maybe Shannon, how do you think this diversity of actors could benefit the development of quantum technologies?
Yes, I think it's crucial actually to have many people with different backgrounds, different interests actually working together on this problem. So as Olivier already nicely explained, this is not a solved problem, how to build a quantum computer. There's a lot of unanswered questions, both scientific and technical. And I think we're at a very interesting stage actually where we need a lot of input from people with different experiences, whether it's in software engineering, electronics engineering, quantum physics, and also the applications, for example, in chemistry research, material science. So I think this is really crucial at this point of the development to have this community actually working together very closely.
Yeah, definitely. And unfortunately, Shaima is not here with us for now, but she's working in a very promising startup. Maybe Jonathan, you can talk about it. But what's the role of small startup companies in the field of quantum technologies? Or maybe of Pascal, if Shaima can't talk about it with us today. Oh, sorry.
Non mais voilà, je vais répondre en français.
Excuse-moi.
Non, mais je t'en prie. Alors, effectivement, le rôle des startups ici, on en parlait avec Olivier dans le train et hier soir encore jusqu'à tard, mais on voit que la startup fait de la recherche, en fait, joue un peu le rôle des laboratoires. Aussi parce que la recherche parce que le sujet en soi des technologies quantiques propose un changement de paradigme. Donc en réalité, l'ensemble des acteurs se saisissent du sujet, évidemment parce qu'il y a des enjeux éminemment importants au niveau des applications. Et je pense qu'il faut comprendre ici ce qui pousse les startups à faire de la recherche, parfois même de la recherche plus avancée, plus deep que certains laboratoires. Donc il y a une fausse concurrence entre les startups et les laboratoires, puisque tout simplement, les technologies qui sont développées par ces startups sont issues de la recherche. Simplement, il y a une agilité, une mobilité, une rapidité de décision que l'on retrouve dans la start-up, qui n'est pas forcément le cas des laboratoires, avec une possibilité de levier de financement qu'on ne retrouve pas forcément aussi au niveau des laboratoires, puisqu'il n'y a pas les mêmes enjeux économiques pour un laboratoire que pour une start-up. Donc il y a un ROI, il y a des investisseurs, il y a un engouement aussi par rapport au risque et aussi par rapport au potentiel. Donc on retrouve, et d'ailleurs Olivier travaille aussi dans cette réflexion de, comment dirais-je, de comparer la période quantique actuelle par rapport aux autres hype, aux autres tendances et aux autres bulles, j'ai envie de dire, technologiques. Donc on est vraiment dans cette tendance actuelle. Et donc il n'est pas étonnant de voir des startups se saisir de sujets et de recherches quasi fondamentales, voire avec un TRL relativement bas, tout simplement parce que les enjeux sont là et il y a encore une fois une réactivité côté startup qu'on ne retrouve pas forcément côté laboratoire. Ça ne veut pas dire que des équipes comme celle de Shannon n'ont pas l'ambition des startups, mais n'ont pas forcément les moyens des startups.
So it means that there is a lot of complementarity between the different actors, the startups and the university. So maybe we can welcome Shaima. Shaima, do you hear us?
Yes, hi Alina, hi everyone. I'm sorry for the technical problem. I'm very happy to be with you, and even if I don't see you, so this is a bit weird. I don't see anyone, but I hope that everything is fine at Strasbourg.
Well, everything's fine. And we were just talking about the importance of startup companies in the field of in the development of quantum technologies. And so Jonathan has spoken about the flexibility of startup companies compared to other big companies or compared to public research. And well, I wanted to ask you, what profile are you searching for with a young researcher? Because you just had your PhD recently in quantum physics, and you're working to develop the business strategy of the Pascal company. So what message do you want to give to young researcher? What type of profile are you searching for in order to develop quantum technologies?
Okay, great. Thank you, Alina. As you said, my name is, I start by presenting myself. My name is Shaima Bouaza. I'm in charge of business development at Pascal. Pascal, it's a startup, a French startup building quantum computers based in Massy and Palaiseau on the Saclay Plateau. It's a very interesting era for the younger generations. They are doing PhDs in quantum physics today because they have this possibility to work in startup working in quantum. And this is a really great opportunity. At Pascal, we develop the hardware, the software, applications, and also the access on the cloud. So we need a wide range of expertise. So physicists, of course, but engineers, because we are building an industrial version of the machine. The product needs to be developed in an industrial manner. This is very important to have the engineers. We are developing applications and combining algorithms from the classical world and quantum world. So data scientists, experts in machine learning, classical machine learning, intelligence, artificial intelligence are a very good fit as well. We are developing cloud infra, the platform to give access to this machine. So DevOps and all the talents needed to develop classical services. In addition, of course, to the business development. So as you said, I'm a physicist, but I'm building the business in Pascal, and this is another direction very interesting to have as well.
Well, thank you for sharing your thoughts with us. I wanted to ask you also, maybe Shaima or Shannon, do you have examples that would speak to people in the audience about the real-world application of quantum technologies, quantum computing? What could it bring? Do you have real-world applications already?
Shannon, you want to start?
Yes, go ahead.
Go ahead,
Okay. Okay, maybe I can present one example we are working on in collaboration with EDF. The problem is simple to explain. We are optimizing the charging of electrical vehicles. We have a fleet of electrical vehicles we would like to charge, a number of charging station available. How can we distribute the vehicles on the available charging stations, taking into account a large number of variables and constraints, and with the goal to optimize the total charging schedule of the full fleet? So, for example, constraints like we cannot put two cars on the same charger, we need to respect the charging duration of each car, etc. And combinatorial optimization problems are among the first use cases we can start developing on the NISC system, so the available hardware today.
Thank you.
So maybe I would add to this also, I think one of the most exciting opportunities in the near term, so for these so-called noisy intermediate scale quantum computers, is probably for scientific discovery. At least that's what excites me the most as a scientist. And there's a very wide range of problems actually, which are either quantum mechanical problems or problems that can be efficiently mapped to quantum mechanical problems, which appear to be very well suited to even the current generation of quantum simulators and quantum computers that we have today. And I think it was even just in the last week, there was at least 3 major publications, 2 from the Google team and 1 from a group in Harvard, which used these, let's say, prototype quantum computers and quantum simulators to, let's say, learn about new phases of matter, so in many-body physics, for example, which is hard, if not impossible, to do using classical computers. And so one of the things that we're very interested in developing here in Strasbourg is to kind of capitalize on our research expertise, which covers many different fields. Compared to where I've worked before, this multidisciplinary aspect in Strasbourg is extremely strong. And there's actually a very broad community of researchers from chemistry, from material science, from computer science, from mathematics, who are all very interested to learn what they can do with quantum computers, what kind of problems they could potentially solve for their research. And I think that's one of the interesting applications in the near term. It can be an enormous boost for scientific research, and then you don't know where this might take us. Yeah.
Well, thank you. And well, you're just speaking about how diverse the profiles are also among the University of Strasbourg. So how do you get people to collaborate? What was the role of the university in making people work together, bringing people further in the field of quantum technologies?
Yeah, that's a very good question. I would say as scientists, we're naturally used to collaborating. I mean, it's part of how we do our work. But there is still very serious, let's say, language barriers or knowledge barriers between these disciplines. And so that's why I think efforts like this by Olivier are particularly useful, because they help bridge this gap. And also meetings like we have today, bringing to many different people together to discuss the open challenges and opportunities, I think is really important. And then we go back to our labs, we go back to our research groups, we start new projects, and I think also having initiatives, let's say at the state, the national level, and also the European level, which aim to stimulate these kind of cross-disciplinary collaborations is really important and very valuable.
Well, thank you for this hopeful yeah, it's a message full of hope. You spoke, Olivier, earlier about all the advantages that could be brought with quantum technologies, the sensing and everything, the sensors, but could you also define what are the limits of quantum computing and the development of quantum technologies? What are the things that we need to
Well, we discussed a bit about that. I mean, there's a limit to scalability. Right now, the big challenge is most of the things which are dealing with quantum computing are unfulfilled promises of scalable computing, because most of the systems available today are not scalable. So the problem is how do you fight noise, how do you fight decoherence, how do you scale those systems, to go beyond the computing capacity of existing classical computers. So it's a mix of science and engineering. People don't agree about the mix. I mean, some people say it's only scientific because decoherence is a very complicated physical process to control. Others, I would say techno-solutionist people say it's just engineering. So it depends of the view. It depends also of the type of qubit. For typically, when you want to control a superconducting qubit, you need to do something very well, which is create microwaves, which are sent to the qubit to control them. But probably, I presume that when you control cold atoms, you need a good laser. You need a good optics. So it's a different kind of enabling technology that you need to have a good control of the qubit and to scale. So it's a mix of science and engineering. On top of that, you need, like we said with our discussion with Kauta, we need to increase the skills in algorithm design, which takes into account the potential and the limits of hardware. So, for example, right now, there are a lot of people who think that most of the algorithms should be designed with the underlying hardware inside, whereas aujourd'hui, today, when you develop a website, you don't care. I mean, you don't care if it's running a processor from Intel, AMD, NVIDIA, whatever. You don't care about it. You do PHP or whatever software you have on your server. So right now, there's a greater link between hardware and software because it's not well optimized. Probably in the future, when these computers will scale, the dependencies will decrease in the future, where you're going to have those Qiskit or whatever other framework which will be relatively independent from the underlying hardware. So there are many different. One of the challenges I mentioned, it's a huge one. It's data loading. Because all the applications which require loading a lot of data in a quantum computer requires both an algorithm engineering, data preparation in the classical side of the system, then optimizing this so-called quantum memory that doesn't exist yet. So it's a lot of bricks to put together. Another example of one huge technology and engineering challenge is many vendors think today that it's going to be difficult to have many qubits in one system because of decoherence and noise and blah, blah, blah. And so what they think is the right approach is to have several small units of computing but connected together with, let's say, in a simple way, photonic link, let's say a fiber. And they think it's going to be a solution to do what we call in classical computing a scale-out architecture. So many systems connected to the other. But this brings new challenges on its own, a new research area, new startups being created. There are already 3 startups in the world working in that path, one in Netherlands, one in Israel, and one in the US. And it's an entirely new area to investigate.
Do you think it's a promising technology? What technology do you think we should
I'm not knowledgeable enough to say if it's promising. It's interesting, but I have not got any proof that it works. So it has to be looked at. That's all I can say.
Okay, it was a bit like the question that you asked earlier. What technology do you think we should focus on, or what are the coming breakthroughs that are going to be made?
Well, one of the reasons why it's difficult to assess the various technologies is the investment in these has not started simultaneously. The oldest ones, I would say, if you look at time, were superconducting and cold atoms. I mean, cold atoms experiments started with Serge Haroche back in the mid-90s. The first control of a cold atom was in about 20 years ago. Superconducting qubits, the first functioning couple of qubits were created back in 2002 by Sewa and Saclay, just after some work in Japan and some work in the US, so 20 years ago. But if you look at another track which I follow very closely, which are electron spin qubits based on silicon, work started just, I would say, 5 years ago. So it's more recent and with longer cycle because it takes a longer time to produce the wafers and the transistors and the so-called quantum dots on these systems. So today it's perceived as, of course, less mature because they even don't know how to untangle more than 5 qubits right now, more or less. So it's very immature compared to the others. But since it's younger, You don't know. Another track, since I'm listing all the technologies, is photons. So you have a lot of interesting experiments done by the Chinese labs on photons. It may be promising. It's got also its problems, its showstoppers, but it's also promising. So you don't know. You don't know.
Okay, well, we'll
And,
follow that.
the lesson of history is very interesting. 20 years ago, the fashionable qubit was called NMR, nuclear magnetic resonance. And NMR, which is also used in medical imaging, was very popular. And back then, the consensus was it was a very promising technology. Now, it's nearly dead in the water. So it means that you can't make a bet today of what's going to work in 20 years. You have to invest in all these different technologies. You have to understand what are their strengths and weaknesses, or sometimes how they can complement each other. For example, cold atoms, let's say it works for computing, fine. But even if it doesn't work, it could be used for quantum memory, some way. So it's a way to use it in another dimension. Take NV centers, which I didn't mention. It's another technology, NV centers. It's a structure of carbon where there's a missing atom replaced by a void, and then you've got a nitrogen atom next door, and then you control the spin of 2 electrons in between. Okay. And this could enable both sensing and computing. But this could enable also quantum memories, because the stability of this spin is very long. So there are people who are trying to use it for computing. There's an Australian startup called Quantum Brilliance. I think they're overselling what they do. But other people are using the same technology for quantum memory. That could be useful. So, and even sensing is already mature with the same technology. So that's why you have to look at the technology with a very broad perspective, a broad eye, and not confine yourself to it works, doesn't work there. It's science is like this. I mean, science is about reusing, reinvention, mix and match things. I think that a lot of progress will come from integration. I mean, mixing and matching different technologies together and create solutions. There's going to be a lot of heterogeneity, I think, in the future. Sorry for the long response, but it's...
It's fine, it's fine. Just express yourself. Well, I think we all understood that it's really important to collaborate and to have a broad look at what's going on in the field. But coming back to the region, the Grand Est region, maybe you could present the different actors in the region that are working for the quantum technology development. Maybe Shannon or Jonathan, si tu veux présenter quelqu'un.
So I can start. Obviously, I'm not the best representative of the region. I've been here only for a few years, but already in just 3 or 4 years, I've seen enormous growth here in Strasbourg and in the region Grand Est in quantum technologies and quantum science. And I think the way it started, which is I think really the best way to do this, is through education, actually. So we're very lucky to have one of the first university research schools in France in quantum here, based in Strasbourg, and it's provided an enormous opportunity to bring together all these different actors and to develop things that we would not do otherwise. So certainly in Strasbourg there's a very strong core. A little bit further out, we leverage very strongly our international links, especially to Germany. So we have very strong partnerships, for example, with the Karlsruhe Institute for Technology in Karlsruhe, KIT, and many other partnerships. Yeah? And then, let's say, in France, in the Grand Est region, there are other research groups, also new initiatives in quantum computing, let's say, for example, in Troyes, very strong center in photonics. In Nancy, they have a center for quantum software and quantum algorithm development. And I think there's really a great opportunity, actually, to bring all of these different actors together to really bring forward the next generation of solutions to some of these problems.
Peut-être juste un complément sur une approche un peu plus localisée, suite à nos discussions d'hier soir. Donc il y a évidemment plusieurs façons de s'impliquer dans le développement de ces technologies. Et s'agissant de Strasbourg et de l'INSA Strasbourg, on a abordé le sujet de la formation, qui sera donc le thème de la prochaine table ronde. du prochain panel, mais il y a aussi ce que les autorités locales et régionales vont décider d'adopter comme politique et comme stratégie de positionnement sur et à l'égard des technologies quantiques, parce qu'on peut être un acteur passif ou un acteur actif, et si on est un acteur actif, est-ce qu'on participe directement au développement des technologies quantiques ou on participe aux applications de ces technologies, ou alors, en étant acteur passif, je suis le premier user, le premier utilisateur final de ces technologies. Et dans ces cas-là, on est passé à côté de l'opportunité de la fenêtre qui nous permettait justement de jouer un rôle. Et pour répondre à l'une des questions de Christophe hier soir, ou peut-être même lors du kick-off, Christophe ou Guillaume ? Guillaume, excuse-moi. Tu vois, Guillaume, c'est que précisément, Olivier l'évoquait, Shannon encore avec la pluridisciplinarité. Le qubit, donc c'est la technologie, donc c'est ok, on comprend, mais il y a toutes les technologies connexes. On en parlait hier avec Eddy sur le LIGO, Virgo, enfin sur comment dirais-je, la mesure des ondes gravitationnelles. Il y a la technologie en tant que telle, et puis il y a toutes les technologies connexes. Et toutes les technologies connexes font appel à toutes les disciplines, j'ai envie de dire. Et donc là, on est à l'INSA Strasbourg, donc sciences appliquées. Je pense qu'en réalité, il ne faut pas se tromper de positionnement. C'est-à-dire que si tu choisis comme postulat d'être un utilisateur final, alors oui, tu peux te poser la question, quel rôle on va jouer à ce développement. Mais si tu t'intéresses vraiment à la technologie, pas en tant que telle, mais quelles sont toutes les technologies connexes, et là-dessus, Michel a fait un travail remarquable, comment dirais-je, de la vue éclatée d'un ordinateur quantique sur les technologies habilitantes. Je vous invite à creuser la réflexion pour justement, et là je m'adresse aussi aux autorités, pour choisir un positionnement très clair qui va conditionner, in fine, la place que va occuper la région Grand Est par rapport au souhait que l'on formule tous ensemble ce matin d'en faire un hub quantique. Et donc là aussi, il ne faut pas se tromper. Enfin, Olivier parlait de l'open source concernant son ouvrage. On parlait des limites des technologies quantiques. En fait, ce qu'il faut savoir, c'est que fondamentalement, personne ne peut prédire si l'ordinateur quantique va exister. D'ailleurs, Olivier vient de faire la démonstration d'un exercice de ce qu'on pensait utiliser pour le calcul, finalement, on va l'utiliser pour la mémoire. On va faire du scale-out, on va faire enfin, peu importe. Ce que je veux dire, c'est que ici, il ne faut pas non plus se tromper dans l'approche de l'engagement des acteurs. Je pense qu'il faut vraiment adopter une approche open source, tout simplement parce qu'il faut s'appuyer sur l'intelligence collective. Tout simplement parce que les enjeux sont majeurs. Et il n'y a pas, je veux dire, tout scientifique qui se respecte aura au moins l'humilité et l'honnêteté intellectuelle de dire « je n'ai pas la solution ». Seul. Et donc toutes les initiatives propriétaires, souveraines, d'où la tribune, donc toutes ces initiatives-là freinent le développement. Et c'est pour ça qu'au sein de la fondation Feynman, nous on opte pour une approche open hardware, open science, tout simplement parce qu'on a compris dès le départ, et là on tire les leçons du passé, et pas uniquement en matière de communication, mais aussi en matière de développement scientifique. On se dit que c'est l'intelligence collective, c'est la mobilisation de la communauté. Alors, quelle qu'elle soit, peu importe l'échelle de la communauté, je pense que l'échelle région Grand Est est une échelle qui se défend. Et il faut l'interconnecter avec d'autres acteurs, et donc il faut avoir cette ouverture, cette ambition, et c'est pour ça que je fais une demande de mariage à Shannon, officiellement, veux-tu m'épouser ? C'est-à-dire, on va collaborer parce qu'il faut soutenir ce type... Non, mais Alina, tu nous as traumatisés avec les maris, les machins, enfin, je suis un peu troublé. Mais il faut soutenir ce type d'initiative, surtout que Shannon coordonne en fait un consortium. Et donc, quel budget faut-il pour pouvoir développer un ordinateur Access ? C'est certainement pas 1 million d'euros. Tu parlais de pocket money tout à l'heure. Je pense qu'il faut aller viser les dizaines de millions, pour ne pas dire les centaines, et il faut soutenir ce type d'initiative. Et là, je m'adresse aussi aux autorités pour avoir une stratégie de financement et d'attirer les investissements sur ce type d'initiative.
Merci.
Oui, un peu engagé, quoi.
Well, no, but it's a very engaged speech you gave. I wanted to ask Shaima, maybe if you're still with us, Shaima. Yeah, she's there.
Yes.
She's there. Yeah, well, you've heard everything that we said about the Grand Est region, how we want to make investment and to facilitate the development of quantum technologies in the region. I wanted to ask you, what do you think of the region in terms of attractivity? Do you think that there are possibilities of collaboration? What collaboration could be possible, do you think, between a startup like yours and the region or the university, public actors?
Thank you for the question. So first of all, I agree totally with Jonathan. No one has the answer alone. We need to collaborate, especially in this phase. The technology is still emerging. We don't have a mature technology. We don't know who will be the winner, as it was said by everyone. So working together, we need to bring in all the stakeholders. All the stakeholders, I mean, the hardware provider, startups like Pascal. We need academia for sure to continue developing the hardware and the algorithms and software application. We need HPC centers because early advantage will come from hybrid solution, quantum, classical, so working with agency in France or other HPC centers in Europe. End users, they need to be included from the beginning because they need to bring in the bottleneck, the problem, the use cases, and also the benchmark with the state-of-the-art classical solution. And to answer your your question or second part of the question about the region, yes, there is a great potential because a great academic research. We have some discussion with Shannon, and I think we can collaborate on a number of topics, and then bringing in other actors from the region and users and universities. I think there are a lot of synergies that can be developed for sure.
Well, it's great to see that there are common ambition about the region and that people are really willing to cooperate. Maybe Kauta, I wanted to ask you, because you made your PhD in Paris, in the Paris region, and you moved to Strasbourg in September, but I wanted to ask you how you feel about being here. Are you willing to work also in the field? Do you want to keep on working in the field? And how are you kind of reassured that we are now speaking about quantum technologies, because I know that you've not been working on quantum technologies since the beginning of the semester, but are you happy to get involved in those kind of meetings, and are you willing to keep on working in the field?
Yeah, of course. I am very pleased to be here among you to talk about this subject, which is very interesting. I did my PhD on quantum machine learning, and my hope is to be able to teach people the quantum computing. I think that it's very interesting to teach students this subject, so they will know the field, and they will also willing to contribute on it, because most of people who are working on machine learning, so we do it only in thesis. We don't have the opportunity to have it as a main course. And concerning the quantum machine learning, I will talk about the interests of quantum machine learning. Normally in the classical version, we are used to work with huge data. Much more data we have, much more the better result we get. So if we have the quantum computer, I think because some problems we cannot treat, we have huge data and we cannot treat all the information in a reasonable time. So with the quantum machine learning, we would able to treat all this information in a reasonable time. But also, as we said, that we have some limits. So for example, for the processing, first of all, we should to transform our data to a quantum state, and which right now with quantum simulator, it takes a long time. And so we should deal with that. And after we should know how to work with quantum algorithms to do the quantum circuits and all that stuff. And what is amazing about quantum machine learning is that quantum machine learning could be considered as a generalization of the classical one, because in the classical version is just like we get only one result, but in the quantum version we have several results at the same time, which is really interesting. And as I discussed already with Olivier, I've done some quantum simulation, and the result that I get, it's much more precise than the classical version. So we don't gain only on speed, but also on precision, and it allows us to have another vision, because the data that we are working on it's not the classical data, but the quantum states.
Okay, so we need teacher to teach it to the new students.
Yeah, I hope that it will be in the future.
Thank you for being here. Do we have more time, or 5 minutes? Okay, well. Okay, does anybody in the audience has a question?
So first of all, thank you for this discussion. You spoke a bit about the role of the region Grand Est in this field of quantum technologies, and it seems like to me that the kind of the education part and the research part is already developed in Strasbourg and in the region, but I was wondering if you could comment on the fact that in France today, startups that work with quantum technologies most of the time are in the Paris region, and yeah, if you could comment on that and maybe say, give your opinion on whether you think that this is something that can change in the near future.
So maybe I can give a little bit of perspective. I mean, it was mentioned already that here in Strasbourg we have this opportunity now to build a new platform for quantum computing, this Access project. And for me, at least, this is as much about building this community and ecosystem as it is about the actual hardware itself. And certainly one of the goals through this Access project is to have the kind of environment, or stimulate the kind of environment that would allow, for example, new startups. And I think one of the best ways to do that is actually through students. Actually, the people we train should be the ones that go out and take their innovative ideas and develop, new opportunities from this. And then concerning the region Grand Est in particular, I think one of the most exciting things for me is this very strong connection to Germany and the rest of Europe that we can really capitalize on, right? And so sort of be a bridge or a hub which is connecting Germany, Switzerland, and France in a way that might be difficult in Paris, or at least it's a unique advantage that we have here.
You can create a startup anywhere, I would say. You need talent, so you have enough schools here and universities to build the talent. You need money. Money can be found. It's easier if you live in the US, it's easier if you're in Paris. The thing you have to think about when you create a startup is not where you are, it's where you want to be. If you are in Strasbourg, or if you are in Grenoble or Bordeaux or whatever, what counts is not that you are in Grenoble and Bordeaux or whatever place in France, it's where you want to sell. If you want to sell worldwide, if you want to sell to the US, it doesn't matter that you are in Strasbourg or in Grenoble or Bordeaux. So you're right that most of the startups so far were created in Paris region, but it's changing a little bit. I know about 2 startups that are being created right now in Grenoble, and they had 0 so far in quantum tech. The most famous outside Paris was Mucans. It's been acquired recently by another company who hopefully is French, called AX Blue, whose headquarters I think is in Paris region, but the company from Mucans is still staying in Bordeaux. So you could have companies anywhere. I mean, it's like the rest of the IT business. It's not special. The discussion is, where do you sell, and do you want to sell in Paris because that's where you have the large headquarters from the large companies? We are not here in the region. And the other option, which some regional startups are choosing, and I think it's the best one, is skip Paris. Just sell outside Paris. I mean, sell in the US, sell in the rest of Europe, go in the UK, in Germany, whatever, but forget Paris. And you know, one of the reasons, and it's unfortunate that I'm taped, but one of the reasons is the large French customers are not the most dynamic in the world for new technologies adoption. That's a fact. I mean, you can measure it, it's a fact. And so if you want to sell to an attractive market, you have to go where the customers are more dynamic, more keen and open to innovation, more keen to adopt risky technologies. And those customers, they are mostly in the north and westbound. I mean, in the US, Canada, in the UK, Nordic countries, in some places in Asia. But France is not that dynamic a market, I would say, and particularly with quantum computing. When I compare, for example, the automobile market, all the German manufacturers, BMW, Volkswagen, Daimler, they all have been trying quantum computing for at least 3 to 4 years. They started to work with D-Wave, now they work with IBM. And if you take Renault and Stellantis in France, they are just starting to think about learning about it now. So it shows why it's important to project yourself, project the company as far as possible, when possible.
Yeah, maybe
Shaima is selling everywhere, of course.
Yeah, maybe Shaima, you want to add some elements also?
Yes, so the reason I'm not with you today because I'm trying to sell somewhere else. I cannot say where, but that's the what we are trying is not to focus on France, not only Europe, but really try to go and look for opportunities where we can find them. And I think one of the lessons we learned from the pandemic is that we can work from anywhere. Maybe not the hardware, okay? But for example, large number of our software engineers, they are working remotely from different places. And then the idea of basing a startup in Paris, Strasbourg, or another region is not that important anymore. What is important is to have an attractive project that can help you attract talent and build a team fascinated by the technology, motivated, and willing to do anything to develop the project. And this is for me, it's the most important thing. Just a small anecdote. After my PhD, I did it in Paris. I'm from the south, from Nice. So after my PhD, I took my stuff and I said, I'll never come back to Paris area. I don't like it. I went back to Nice and I stayed there. But then with a job opportunity, I had to go back, and if I have other opportunities somewhere else, I won't think about it twice. So I'm pushing to have Pascal, Côte d'Azur, but they are still resisting. We will see about this.
Thank you, Shaima. Do you have other question, last question, before to pass to the second round table? Okay. So I would like to say thank you to all the experts coming today for us and for this opportunity to exchange with them. And I invite near me right now Foundation. Make some welcome to her. Thank you. And together we are going to introduce the second roundtable experts. So let me introduce Eddy Esmiguer, which is a professor to INSA Strasbourg, and he's training quantum group of students here to Strasbourg, to INSA. So welcome, Eddie. Thank you.
On continue en anglais? Okay. So let me introduce Guillaume. Guillaume, who is a physician and a researcher in biophysics, and he is also teaching here in INSA Strasbourg.
We will continue with Michel Kurek, which is an expert in ecosystem quantum, and he's also the vice chairman of Feynman Foundation too. So thank you for coming, Michel.
Okay. Denis, can you join us? Denis Cavallucci is a research director at iCube. Am I right? Yeah. And he works, he's been working for 25 years on inventive problem solving, and he's going to help us to see how we can make the step to the innovation.
And we have also Cyriac Genet with us. Thank you for coming. He's a professor to ISIS, and also he's training in quantum too from some years. So thank you for coming, Cyriac. And yes, I will let the floor to Rachel and also the expert from this round panel speaking about trainings and also the innovation system. It will be in French, so enjoy it because we are in a French region, so I will let the floor to Rachel. Thank you.
Nevertheless, if someone needs the translation, we can also make the effort. Merci et bonjour tout le monde. Alors, je voudrais commencer par des petites questions à l'audience, parce que c'est facile et parce que j'ai un échantillon assez représentatif et surtout intéressant pour moi parce qu'il introduit un biais qui va me permettre de lancer cette table ronde, ce panel. Alors, qui dans la salle, vous allez voir, c'est très très facile, qui dans la salle s'est déjà intéressé au quantique? Merci. Qui pense utiliser ces technologies un jour? Merci à nouveau. Alors maintenant, une petite question peut-être un peu plus... il y aura peut-être moins de mains levées. Et si quelqu'un est juste prêt à me répondre en 2 ou 3 mots, mais pourquoi? Pourquoi vous intéressez-vous au quantique et pourquoi pensez-vous, ou comment pensez-vous utiliser un jour les technologies quantiques? Si quelqu'un est capable de me donner un élément de réponse rapide. Oui, mademoiselle? Non? Monsieur derrière? Oui.
J'ai aucune autorité en la matière, hein, mais moi je suis un enseignant en informatique et je m'intéresse un petit peu au champ quantique pour 2 raisons. D'abord, il semble pour un béotien que ça induit de nouveaux phénomènes physiques qui sont très contre-intuitifs. Et donc, je pense que c'est intéressant, au même titre que la mécanique newtonienne a fait apparaître. On a ça en nous. On réfléchit à notre vision du monde au travers de cette culture-là. Et je pense qu'il est intéressant pour la même raison d'avoir une connaissance de la mécanique quantique parce que ça va sans doute avoir des répercussions technologiques, on vient d'en parler. Et comme pour la mécanique newtonienne, il est important d'avoir un petit peu la base de connaissances générales qui permettent de voir un petit peu sur quoi c'est basé. Ça, c'est le premier point. Et puis, bon, comme je suis enseignant en informatique, je regarde un petit peu ce qui se passe au niveau du quantum computing, en pensant que je serai à la retraite quand ça sera réellement effectif, mais par intérêt professionnel à ce moment-là. Voilà.
Merci beaucoup pour vos réponses. Ce que vous dites, je crois, va bien lancer le sujet, parce que justement, ce qu'on fait aujourd'hui, c'est qu'on pose les bases de technologies qui vont servir pour les futures générations. Et donc, ma question maintenant, la question qui va guider ce panel, c'est comment pourra-t-on passer de cette formation initiale à l'innovation et donc à l'avènement du quantique dans nos vies quotidiennes dans le futur. Donc nous sommes aujourd'hui à l'INSA. Cet événement est organisé en partenariat avec l'Université de Strasbourg. Et j'ai entendu dire que, Guillaume, qu'à l'INSA, c'est une école de sciences appliquées, mais néanmoins, on enseigne encore la physique du XVIIIe et du XIXe siècle. Et donc voilà, ma question que je pose à Guillaume, et puis Eddy complétera peut-être, c'est comment réconcilier cette physique du XVIIIe et du XIXe siècle avec cette ambition de transmettre l'appétence ou les compétences nécessaires pour le quantique.
Donc oui, c'est vrai que l'essentiel de la physique qui est enseignée ici à l'INSA de Strasbourg est de la physique classique et de la mécanique qui utilise encore même des outils qui ne sont pas à la pointe de ce qui se fait en physique théorique, par exemple aujourd'hui. C'est des outils qui sont nécessaires pour faire de l'ingénierie d'aujourd'hui. Et parce qu'il n'y a pas que l'innovation aujourd'hui, il y a aussi, c'est important de parler de... je sais que l'innovation est un terme très populaire, mais il faut aussi parler de la maintenance. Il faut aussi parler du fait qu'il y a des compétences aujourd'hui qu'il faut garder et qui sont nécessaires pour le développement de l'innovation, justement. Il n'y a pas que besoin d'être dans la pointe, il faut aussi savoir maintenir une connaissance. Et ça, l'INSA de Strasbourg le fait très bien et est capable d'aborder des sujets qui sont pointus et spécialisés, mais qui nécessitent de la physique qui n'est pas nécessairement de la physique moderne. Alors, je pense que c'est important de dire aussi que ce n'est pas du tout contradictoire d'avoir ces enseignements-là simultanément avec des enseignements d'introduction, c'est ce qu'on fait aujourd'hui avec Eddy, d'introduction aux problématiques de physique quantique, alors plus exactement de calcul quantique. C'est ce qu'on fait ici à l'INSA. On a peu d'enseignements en informatique, on n'a pas de filière spécialisée là-dedans, donc l'approche d'introduction au calcul quantique reste très superficielle, mais elle ne nécessite pas de connaissances pointues en physique, justement. Donc c'est pour ça qu'on a choisi cette approche-là. Si on voulait faire de la physique quantique à proprement parler, alors là, on aurait besoin d'avoir un cursus bien plus prononcé. Mais ce qui existe aux universités et ce qui est mené ici à l'Université de Strasbourg. Donc je pense que faire de l'introduction, sensibiliser à ces problématiques est tout à fait possible dans le cadre d'un établissement d'enseignement qui pourtant porte son attention sur de la physique plus ancienne.
Eddy, un petit mot sur peut-être...
Oui, je peut-être compléter un peu. Si on prend ce qui a vraiment changé notre monde moderne, c'est l'informatique, mais au sens classique. Et la chaîne scientifique qui va depuis la physique fondamentale jusqu'à l'ordinateur, disons, on va dire conventionnel, hein, les processeurs qu'on a dans nos smartphones ou nos ordinateurs, c'est aussi une longue chaîne qui connaît plusieurs transitions de phase. C'est-à-dire que ça commence par la mécanique quantique aussi, puisque dans les semi-conducteurs, il y a la théorie des bandes, qui est la résolution de Schrödinger dans le potentiel périodique d'un cristal. Ensuite, une fois qu'on a fait ça, il faut ramener la physique statistique pour décrire le comportement des porteurs de charge dans ce type de semi-conducteur. Ensuite, il faut poser les bases des semi-conducteurs intrinsèques, puis extrinsèques, et ainsi de suite. Et ce que nous, on enseigne ici à l'école, tout au moins pour une partie des étudiants, notamment les génies électriques, c'est plutôt des enseignements, bien sûr, qui s'appuient sur cette physique fondamentale, mais qui font quand même l'économie de ce niveau de description. En d'autres termes, nous, on intervient en électronique numérique classique, digital electronics, avec un niveau d'abstraction où on dit que les bits sont à 0 ou à 1, sans tellement mentionner quel est le support physique de cette information qui a été rendue un peu abstraite. Donc c'est le domaine du génie électrique. Alors effectivement, avec Guillaume, on a décidé d'abord parce que, en tout cas en ce qui me concerne, c'est ma compétence, et aussi parce qu'on ne peut pas tout faire, plutôt de se raccrocher sur, en gros, l'équivalent quantique de ce qu'on appelle le digital electronics. C'est-à-dire c'est la description sous forme de portes élémentaires des algorithmes type Grover, Shor, etc. Alors c'est clair que selon le profil des étudiants, ils vont avoir accès à ce niveau de description plus ou moins facilement. Alors, juste pour donner quelques compléments d'information, on a, nous, donc un cours de 2 ECTS, c'est pas énorme. On avait, je crois, 25 ou 26 étudiants, et ils étaient majoritairement dans des spécialités, donc 2 spécialités, génie électrique et mécatronique, où ils étudient le digital electronics. Et il faut bien reconnaître que, disons, le niveau, moi je m'appuie souvent sur la comparaison avec les portes élémentaires, les portes NAND, les portes OU, etc., classiques en électronique conventionnelle, pour développer ce cours. Et j'ajoute aussi que des connaissances en traitement de signal sont utiles, parce qu'il y a aussi une acquaintance forte avec cette discipline-là. Ça suppose quand même, quand bien même, bien sûr, il faut continuer d'enseigner la bonne vieille physique, il y a quand même aussi de temps en temps des ruptures didactiques. Je prends juste un exemple, mais sans rentrer dans le détail. Quand l'humanité a commencé à faire du traitement du signal, elle l'a fait avec des outils analogiques, parce que c'était les outils qui étaient disponibles. Ça a donné les ampliopes, etc. Et donc, le système d'écriture a dû décrire les phénomènes dans un monde analogique, et ça a donné l'intégrale de Fourier pour la transformer de Fourier. Mais aujourd'hui, c'est daté, parce qu'aujourd'hui, le traitement du signal se fait de façon numérique. Donc, on n'a plus besoin d'enseigner au même titre l'intégrale de Fourier, puisque dorénavant, elle est traitée de façon numérique. Et je pense que là, il y a un parallèle à faire avec le quantum computing. Computing, je dis bien. Nous, on s'intéresse en fait à des systèmes qui sont dans une superposition d'états quantiques, mais dans un espace de dimension finie. Tandis que les physiciens, eux, ils regardent position et vitesse, qui sont des variables qui sont dans des espaces de dimension infinie. Et ça fait une grosse différence. Et c'est pour ça aussi que ça devient raisonnable de proposer ça à des étudiants qui n'ont pas forcément un niveau particulièrement élevé, parce que le système d'écriture, ça commence par des vecteurs dans le plan. Or, le vecteur dans le plan, a priori, des lycéens peuvent déjà avoir une introduction très précoce à la physique, enfin, en tout cas au quantum computing.
Merci. Alors, ma question suivante, mais vous l'avez un peu déjà abordée, était sur INSA, École de sciences appliquées, génie mécanique, génie électrique, génie climatique, génie énergétique, et j'en passe, génie civil. Et comment intéresser les étudiants, puisque le quantique est une science qui cherche encore ses applications, comment intéresser les étudiants au quantique quand ils sont venus pour faire des sciences appliquées?
Il y a une réponse très simple, c'est que c'est passionnant. En fait, déjà, la physique quantique en elle-même, c'est des observations qui défient généralement l'intuition, mais j'ai envie de dire que si on les apprend tôt dans sa vie, eh ben, je pense qu'on arrive à construire une intuition et qui, en même temps, permet d'aborder un domaine de la science qui est vraiment qui est passionnant, tout simplement. Moi, en tant que physicien, j'adore ce domaine-là. C'est vraiment quelque chose qui est facile à passionner les foules. Alors, en plus, la physique quantique qui est introduite, d'introduction généralement, permet très vite de rentrer dans le vif du sujet, rentrer dans des observations qui sont passionnantes. Après, si on fait un peu de la mécanique quantique 2, je sais pas, le deuxième module, c'est toujours un peu plus dur. Je parle d'expérience, mais je pense que c'est facile de partager cette passion avec les étudiants. Donc ça, c'est mon point de vue pour la physique quantique. Pour le calcul quantique, vraiment je pense qu'il est important de distinguer, c'est pareil. C'est pareil parce que, comme l'a dit Eddy, on peut toujours se baser sur l'expérience qu'ont les étudiants avec les portes classiques, et puis de commencer à leur dire non mais regardez ce qu'il est possible de faire, c'est un peu plus mathématique et c'est un peu plus difficile de voir la beauté de la discipline, mais je pense que c'est vraiment via ce biais-là qu'il est facile d'intéresser les étudiants.
Merci. Monsieur Cyriaque-Genet, les chercheurs ex-étudiants qui arrivent dans votre labo au CNRS, qu'est-ce qui les a amenés ici, qu'est-ce qui les a motivés pour se lancer dans ces sphères de recherche?
Alors c'est vrai que nous, dans les laboratoires, moi je parle en tant que physicien, on fait de la physique fondamentale dans nos laboratoires, on accueille essentiellement des étudiants qui sont formés dans des cursus de physique fondamentale. Donc notre école doctorale QMat est une école doctorale qui forme des physiciens fondamentaux aux problématiques de sciences quantiques. Et c'est essentiellement ces étudiants qu'on accueille, d'abord en master, puis en thèse. Et ce qui change aujourd'hui, et ça recoupe assez bien vos analyses, c'est que les expériences qui sont devenues de plus en plus quantiques, on peut dire, c'est-à-dire, vous verrez peut-être tout à l'heure les salles de manip de Shannon Whitlock à l'ISIS, donc c'est ces expériences qui impliquent plusieurs composantes de physique expérimentale simultanément autour d'une même table optique. Donc on peut partir de l'ultravide, aller vers la spectroscopie des atomes, le refroidissement d'atomes, la physique des lasers et toute l'électronique qui va avec pour le traitement de données, en fait, à diversifier le profil des étudiants qu'il est nécessaire de pouvoir héberger dans les laboratoires. Et c'est là où effectivement il peut y avoir un recouvrement très important et très intéressant entre les cursus fondamentaux qu'on trouve à l'université et les cursus ingénierie qu'on trouve dans vos écoles. Par exemple, des étudiants très bien profilés en traitement du signal et en analyse de données ou en électronique bas bruit, par exemple, c'est des étudiants qui deviennent extrêmement précieux dans nos laboratoires. Parce que le signal quantique est souvent un signal faible. L'analyse des caractéristiques quantiques du signal, elle présuppose effectivement une certaine connaissance et compréhension du traitement du signal en tant que tel, et ce n'est pas forcément un étudiant d'un cursus fondamental qui est préparé à ça. Par contre, là où effectivement je constate une tension chez nous, les physiciens fondamentaux, c'est sur ce qu'on appelle les fondamentaux de l'enseignement de la physique. On ne raisonne pas en physique du 17e, 18e par rapport à la physique quantique. On parle de la physique comme une science cohérente et on pense encore aujourd'hui qu'il est important, par exemple, de faire de la mécanique des fluides ou de la physique statistique classique pour être armé, pour avoir les outils, notamment dans la réflexion analogique vis-à-vis des problèmes de physique quantique qu'on va rencontrer au laboratoire. Ça, c'est un point qui perdure, qui reste, mais qui est très fort, je dirais, uniquement dans les cursus fondamentaux. Mais c'est aujourd'hui des discussions très fortes parmi les collègues. Là, ce que vous parliez c'est vous qui parliez de ces changements un petit peu voilà, cette transition de phase dans l'enseignement. Aujourd'hui, on les appréhende de manière critique. On les a eus il y a une vingtaine d'années avec les systèmes dynamiques, quand le chaos était arrivé comme ça dans la physique. Il y a eu des grandes modifications. Là, on en est à ce point-là. Et c'est des discussions intéressantes.
Merci. Je me tourne maintenant vers Michel, donc Michel Curec, qui a travaillé, alors apparemment on ne va pas pouvoir la projeter, mais qui a travaillé sur un framework des compétences, parce qu'on parle de complémentarité des compétences et d'interdisciplinarité. Et je voudrais, Michel, si tu peux nous en dire un mot, nous dire un peu ce que tu as réussi à esquisser, qu'il va falloir qu'on imagine mentalement.
Une chose est claire, hein, et on retrouve ce point-là dans vos discussions, c'est que là on parle de physique quantique, d'ordinateur quantique, de technologie quantique, on est sur de la multidisciplinarité. On a besoin de chercheurs fondamentaux avec tous les aspects des compétences reliées à la recherche fondamentale. On a besoin de praticiens avec une grosse partie d'ingénierie. On a besoin pour certaines technologies de qubits de spécialistes du froid, de cryogénie, d'électronique, comme vous le disiez, à bas bruit dans des réfrigérateurs à dilution où la température règne à moins de la température de l'espace. On est à 15 000 Kelvin dans ce type de qubits. Donc on a besoin d'ingénieurs capables de monter ce type d'appareillage, de les faire fonctionner, de les calibrer au quotidien. On a besoin d'électroniciens classiques, je dirais, avec des appareillages qui fonctionnent à température ambiante. Et après, il y a tous les champs liés aux technologies quantiques qui vont se baser sur effectivement à la fois des compétences d'ingénierie et à la fois des compétences de physique fondamentale. Des gens qui vont se spécialiser dans l'ordinateur quantique, qui vont se spécialiser dans les capteurs quantiques ou dans les télécommunications quantiques ou dans les simulations, avec parfois évidemment des interconnexions entre ces différents domaines. Et on se rend compte que plus on rentre dans le détail, plus on est capable de mettre en exergue quel type de compétences, d'aptitudes on va rechercher suivant le métier dont on a besoin. Et de toute façon, pour créer une start-up, si un jour vous lancez dans une aventure entrepreneuriale, ce qui sera important, c'est de constituer une équipe multidisciplinaire, interdisciplinaire, et ce sera la qualité de la start-up. Si vous avez 10 personnes qui ont exactement la même compétence, ça ne va pas aider dans beaucoup de développement commercial de la start-up. Donc il vous faudra aussi des soft skills, on en parle beaucoup, mais on n'en parle pas beaucoup, mais il faut du soft skills, de la programmation classique aussi, puisqu'au final, beaucoup des langages utilisés en informatique quantique ressemblent à du Python. Donc un informaticien Python peut très vite et rapidement rattraper un retard s'il n'a pas eu en formation initiale ce type d'enseignement.
Merci. Alors, du coup, comment permettre la rencontre de ces compétences et à quel moment ça commence ? Le sujet de ce panel, c'est de la formation initiale à l'innovation. Donc, en termes de formation initiale, à quel moment on commence ? Je sais que vous avez dit que vous êtes allé dans quelques lycées, que vous avez commencé à en parler à des lycéens, donc même avant la formation initiale. Si vous pouvez juste nous en dire 2 mots et nous dire ce qui les a interpellés dans votre intervention et dans votre présentation du quantique.
Alors, par rapport à ce que disait Guillaume, je crois que la physique quantique et la physique moderne, de façon générale, elle est un petit peu à double tranchant, en ce sens qu'à la fois elle fascine, parce que pour beaucoup, ça paraît un peu de la science-fiction, ça retourne le cerveau, comme on dit maintenant, c'est tellement ça nous sort de notre expérience quotidienne. Mais du coup, en même temps, elle a aussi la réputation d'être difficile, en ce sens qu'elle est écrite dans un langage qui est quand même pas si facile que ça, c'est les mathématiques. Et ça rebute souvent. Donc, alors j'ai fait 2 expériences dans des lycées où j'ai expliqué un petit peu que le photon, il n'y a pas de demi-photon, donc le photon doit être décrit par un vecteur, et ce vecteur, dès lors qu'on parle de 2 états quantiques, dans le qubit, ça se ramène il est dans une combinaison linéaire de 0 et de 1, ça se décrit avec un vecteur dans le plan. Et le vecteur dans le plan, on a tous appris ça au lycée. Et depuis la réforme du bac, eh bien, nos jeunes lycéens sont de nouveau un peu plus formés aux maths formelles dans leur classe de terminale. Donc ils sont fascinés. En même temps, sans doute, comme c'est comme les interventions assez courtes, ils peuvent avoir l'impression de comprendre, mais en réalité, quand on leur demande de reformuler dans leurs termes, c'est difficile et c'est normal, parce que à toutes les fois qu'on est confronté à la nouveauté, en réalité, à la première lecture, il ne reste pas grand-chose. Et pourtant, cette première lecture, elle est bien nécessaire, avant qu'il y en ait d'autres. Donc, je fais ça suite à... Je crois que c'est le MIT qui a aussi décidé de faire des expériences d'enseignement précoce. Parce qu'encore une fois, les niveaux de description existent. Ils ne sont pas si coûteux que ça. En revanche, et c'est là qu'il y a vraiment cette ubiquité aussi du domaine, il faut renoncer, et ça c'est un deuil à faire, il faut renoncer à une interprétation qu'on peut décliner dans les langues naturelles. Quand on dit le photon, il est simultanément au-dessus, en dessous, dans les bras d'un interféromètre, tout ça c'est des pis-aller, mais en fait on ferait peut-être mieux carrément de les éviter et de directement embrayer sur finalement quelque chose qui est quand même assez accessible, c'est le vecteur dans le plan. Donc il y a ces soucis. Et maintenant, la question que je peux poser à un physicien praticien de longue date, c'est est-ce qu'un jour on peut arriver, à force de fréquenter le système d'écriture, est-ce qu'on finit par penser quantique, comme si on développait par une sorte de mutation et disons d'évolution accélérée par la fréquentation quotidienne des calculs, est-ce qu'on pense quantique comme un photon? Ça, je ne sais pas. Moi, ce n'est pas mon cas, parce qu'on a une année d'expérience. Mais peut-être qu'à force de fréquenter le système d'écriture, et ça marchera d'autant mieux que c'est fait tôt, comme un enfant apprend beaucoup plus facilement une langue étrangère lorsqu'il a une assimilation précoce.
Je vais poser une autre question à Denis qui va peut-être permettre de cheminer sur le parcours d'un étudiant jusqu'à ses premières expériences professionnelles. Vous enseignez depuis quelques années déjà le quantique. Et est-ce que vous avez un retour sur les premières expériences professionnelles de vos anciens étudiants? Et voilà, comment ont-ils utilisé ces apprentissages?
Alors, déjà, je voudrais remercier les organisateurs de m'avoir donné l'occasion de témoigner à cette table ronde, répondre à votre question. Alors, tout de suite, d'emblée, je ne suis pas expert du quantique. Je suis très très nouveau dans le domaine du quantique. Ce n'est pas un domaine de spécialité. Je ne suis pas non plus un physicien, ni même un expert en physique, ni même en chimie, ni même en mécanique. Alors, vous allez vous poser la question, mais vous êtes expert en quoi alors? Ben, je suis expert dans un mot que j'ai beaucoup entendu dans le discours de ce matin, à la fois dans le discours qu'a tenu Olivier, mais aussi dans la table ronde qui a suivi, c'est que je m'intéresse particulièrement au problem solving, à la multidisciplinarité et au fait que j'identifie que le mot-clé ou le mot problème est probablement le mot qui est statistiquement le plus souvent revenu dans tous vos discours. Ça tombe bien, c'est ce que j'enseigne à l'INSA, c'est que ce qui m'intéresse particulièrement, c'est l'aptitude de nos scientifiques, de nos étudiants, de nos ingénieurs à formuler et résoudre les problèmes. Et pourquoi je pense que c'est un préambule indispensable au progrès du quantique dans le hub strasbourgeois, c'est parce que le monde du quantique en lui-même va se trouver face dans les 2 ou 3 prochaines décennies à une avalanche de problèmes à résoudre dans tous les domaines. Et aujourd'hui, vous n'avez pas 36 000 façons de résoudre les problèmes. Vous faites du brainstorming, vous faites des essais et des erreurs, ou vous faites du googling. Alors, moi je suis contre ces 3 approches et je pense que l'aptitude à identifier et formuler les problèmes, il faut quelque part une forme de science de l'invention qui particularise le fait que par rapport à un ensemble de connaissances existantes sur un sujet, ben, nous pourrions automatiser l'identification et la formulation des problèmes à résoudre, toutes disciplines confondues, et aller chercher là où se trouve la réponse dans la science et la physique, des réponses potentielles aux problèmes qui se posent. Alors ça présuppose une science de l'invention qui dépasse les clichés classiques du brainstorming quand on est en recherche de problèmes solving. Alors, dans la capacité à l'INSA d'enseigner le problem solving, qui reste quand même une des compétences clés attendues chez l'ingénieur, eh bien, il faut quelque part en passer par une forme de science de l'invention. Et je suis persuadé que c'est une des clés pour le quantique et pour d'autres domaines disciplinaires que d'apprendre aux jeunes à formuler et résoudre les problèmes de façon pluridisciplinaire et non pas de façon intuitive, uniquement intuitive ou reposant sur des informations qu'on aurait pu glaner ça et là en lecture d'articles scientifiques ou autres.
Je crois que ça répond donc à une question aussi posée ce matin dans la séance introductive par Olivier Ezratty, la question de l'innovation dans la façon dont on enseigne. Voilà, comment innover dans la façon dont on enseigne pour faire émerger de nouveaux usages, pour faire émerger, voilà, on parlait de use case, etc. Et probablement que votre approche voilà, répond
alors,
partiellement...
Il y avait des pistes ce matin, mais il ne les a pas dites. Hein. Là, je vais vous en donner quelques-unes, même si je ne suis pas expert
on
du
est
quantique.
friand.
Je pense que les réponses aux problématiques du quantique, elles n'arriveront pas du quantique ou des experts du quantique. Je pense qu'il va falloir aller chercher de l'information ou de la connaissance en dehors du domaine du quantique pour résoudre les problèmes du quantique. Alors, où va-t-on? Sachant que le quantique, on peut considérer qu'il est sur le leading edge des sciences et des techniques, donc ça ne va pas être évident de trouver des découvertes scientifiques tous les matins pour solutionner les problèmes du quantique. Peut-être qu'il faut aller dans un domaine disciplinaire comme les sciences de la nature. Peut-être qu'il faut faire du biomimétisme. Mais l'approche pluridisciplinaire pour résoudre un problème du quantique par aller chercher l'information là où elle se trouve, je pense que c'est une des clés et il faut bien évidemment, pour pouvoir la pratiquer au niveau de l'ingénierie, l'enseigner à nos étudiants et à nos chercheurs.
Bon, alors on me signale qu'il faut, qu'il faut faire vite. Donc je passe à la question suivante qui est justement... Donc, on a déjà déjà bien traité de la partie formation et on chemine là vers l'innovation grâce au problem solving. Comment on s'en sort aujourd'hui en France en termes d'innovation dans cette course au quantique? Voilà, Michel, exactement, la question est pour toi. Olivier parlait ce matin d'invisibilité française. Qu'est-ce que tu peux nous en dire?
Alors, en termes de métriques, première chose auquel on peut penser lorsqu'on on étudie l'innovation, c'est regarder les brevets. Denis, c'est sa source d'information principale, c'est une source une des sources. Regarder les brevets, c'est aussi regarder tout ce qui est publié, c'est regarder les publications scientifiques sur les sujets. Donc c'est une étude que j'ai menée il y a quelques mois qui m'a permis de positionner un petit peu la France, l'Europe, par rapport à deux pôles que sont les États-Unis et la Chine. Il faut savoir qu'aujourd'hui, la Chine, dans le domaine des technologies quantiques, publie plus de 50% des brevets. Si on prend toute l'Asie, en intégrant le Japon et la Corée, l'Asie publie 64% des brevets. Si maintenant je prends juste la Chine et les États-Unis, j'ai 75% des brevets. Donc ça laisse très peu de place pour l'Europe. L'Europe, en prenant les frontières les plus larges, on arrive à 13% des brevets. C'est une situation très paradoxale puisque en termes de publications scientifiques, l'Europe compte pour 43% des publications sur les technologies quantiques. Donc on a ici quelque chose, une situation un peu paradoxale qu'il va falloir résoudre. Comment, certainement en aidant les chercheurs à trouver des solutions à leurs problèmes, les acculturer pour certains pays comme la France qui est un peu en déficience par rapport à l'Allemagne, le voisin le plus proche ici, les acculturer à l'importance de la propriété industrielle lorsqu'il va s'agir de commercialiser des inventions. Donc l'innovation, on voit que c'est aussi une partie business. On a une acculturation différente dans la partie commercialisation des capacité de commercialiser des découvertes. Lorsqu'on regarde le monde anglo-saxon, la facilité qu'ont les startups anglo-saxonnes à lever des fonds de la part de Capital Venture et comparé à ce qu'on trouve ici en Europe, c'est le jour et la nuit. Donc il y a des travaux à faire aussi en termes d'acculturation du capital risque français, qui n'est pas très enclin à prendre du risque, contrairement à l'anglo-saxon. Donc il y a beaucoup de travaux à faire, on le voit sur ce chantier, de la petite école, ou en tout cas peut-être de la classe prépa, pour aussi les initier à vouloir prendre des risques, à avoir cette aventure entrepreneuriale qui pourra effectivement faire en sorte que la France puisse aussi, et l'Europe puisse reprendre une position plus équilibrée par rapport aux États-Unis et à la Chine. Je vais vous donner juste un dernier point. Si l'on regarde le nombre de brevets déposés dans les 3 principales régions du monde, en Chine, aux États-Unis et en Europe, et qu'on regarde d'où viennent ces brevets, 90% des brevets chinois sont déposés par des entreprises chinoises. Aux États-Unis, 65% des brevets déposés aux États-Unis le sont par des entreprises américaines. Et en Europe, seuls 30%, moins de 30% même, des brevets déposés en Europe le sont par des entreprises européennes. Donc il y a encore une déficience en Europe. Je veux insister là-dessus parce que c'est vous, jeune génération, qui allez faire changer ça, j'espère. Et en tout cas, il faut que tout le monde ait conscience qu'il existe des méthodes pour améliorer ces ratios. Et l'Europe, effectivement, très bien positionnée, comme on le voit par rapport aux publications scientifiques, mais on a une défaillance par rapport à d'autres critères.
Et Strasbourg est très bien positionné en Europe. Donc ça sera ma dernière question, voilà, sur Strasbourg, dans son écosystème, dans la région Grand Est, mais aussi avec les relations transfrontalières et les échanges dans ce collectif. Alors comme on n'a pas beaucoup de temps et puis qu'on en a déjà un peu parlé, moi je vais avoir une question qui j'espère n'est pas une question piège, mais est-ce que l'un de vous a un exemple d'événements passés ou à venir ou si ce n'est pas un exemple, une idée d'événements qui rassemblerait justement cet écosystème, des représentants divers de cet écosystème européen à Strasbourg? Je savais que c'était une question piège, mais on n'a pas le temps de parler longtemps, alors. Oui, bien sûr.
à Strasbourg, et il me semble que Shannon en était un des co-organisateurs. Il y a eu une école d'été de physique quantique qui a été organisée il y a 2 ans et qui a rassemblé tous les participants au réseau ECOR. Vous savez, il y a un grand réseau interuniversitaire le long du Rhin, et beaucoup de laboratoires et de centres de physique quantique sont impliqués dans un même effort, et ça a été un événement où tous ces laboratoires se sont retrouvés autour d'étudiants pour une session de 15 jours fin août. Ça, c'est un exemple.
Super, merci. Alors, il y en a peut-être d'autres, du coup. Ou des idées, ou des événements programmés.
Pas vraiment sur le quantique directement, mais je dirais qu'on a une chaire industrielle en conception inventive à l'INSA Strasbourg, et puis on organise régulièrement des événements sur le domaine du problem solving, et la nécessité pour des industriels de aussi nous renvoyer l'image de ce qu'ils aimeraient qu'on conçoive pour eux dans leur aptitude en R&D à automatiser ces processus et les rendre plus efficients. Bon, on est un peu à côté du sujet du quantique, mais j'attends avec impatience qu'un jour une entreprise du quantique vienne dans cette chaire pour y contribuer aussi.
Merci. Michel, tu voulais ajouter quelque chose?
Je voulais juste rajouter quelque chose et faire le lien avec un modèle dont Olivier a cité le nom tout à l'heure, qui était le modèle de Bohr, qui est un modèle un peu désuet de positionnement d'électrons autour de l'atome. Certes, Strasbourg est à la périphérie de la France, mais du coup, elle se distingue par son énergie, comme dans le modèle de Bohr. L'électron plus éloigné, plus il a d'énergie. Donc je pense que cet événement aujourd'hui va lancer de nouvelles actions au niveau du hub strasbourgeois. On peut penser à l'organisation peut-être de hackathons avec s'il y a des filières informatiques dans l'univers strasbourgeois. On peut penser à d'autres événements comme celui-ci. Donc la limite n'est que liée à l'imagination qu'on peut avoir autour de ça.
Non, et je crois qu'il y a beaucoup d'imagination dans cette salle. Merci beaucoup. Est-ce qu'il y a des questions avant qu'on termine cette session ce matin? Non? Bon. Ben, merci beaucoup. Bonne journée à tous et à bientôt.
Merci beaucoup aux participants de la table ronde. On va vite fait donner la parole à Madame Isabelle Kuhn qui va clôturer notre matinée. Et on est très ravis que la région Grand Est elle est à nos côtés, justement pour exprimer en fait quels sont peut-être les prochains événements, quels sont les prochaines, on va dire, actions ou petits événements qui nous attendent en fait dans notre région. Voilà, je laisse la parole à Isabelle. Merci.
Merci Alina. Alors très rapidement, parce que je pense que votre temps est compté à toutes et tous. D'abord vraiment merci. Le premier constat, c'est que j'aurais appris beaucoup de choses ce matin. J'aurais progressé dans ma connaissance des enjeux du monde du quantique. Ça, c'est le premier point. Le deuxième point, je suis confortée également dans la légitimité de la région Grand Est à se positionner sur ce sujet. Nous sommes déjà aujourd'hui en contact avec Neila Brook, qui nous a identifiés comme une des régions à fort potentiel sur ce sujet. Donc on en prend conscience de plus en plus. Nous avons des contacts réguliers maintenant avec certains d'entre vous à Strasbourg, mais également à Nancy et à Troyes. Et ce qu'on constate, c'est bien entendu, au-delà de ces expertises, au-delà de la multidisciplinarité qui existe et qui est une vraie force, c'est aussi cette envie de travailler ensemble. Et je pense que pour arriver à faire de la région Grand Est un hub dans le domaine du quantique, quand on se place à l'échelle mondiale, voilà, on est tout petit en fin de compte. L'un des éléments clés va bien être de créer ce collectif et de travailler tous ensemble pour faire avancer la région sur ce sujet. La faire avancer, pas de manière isolée, ça a été dit également, connectée au niveau national bien entendu, mais aussi, et j'ai envie de dire, surtout européen, parce que c'est un élément différenciant fort. Nous sommes placés au cœur de l'Europe. On a initié une approche à partir de l'intelligence artificielle qui est une notion de vallée européenne. Alors on l'a beaucoup cultivée en tant que vallée européenne de l'intelligence artificielle, donc en partenariat avec nos amis suisses, allemands, luxembourgeois, belges. On a commencé à créer cette dynamique. C'est 3 ans de travail au niveau politique et au niveau opérationnel pour qu'il y ait une envie à ce que tous ces partenaires travaillent ensemble. Alors il y a déjà de beaux exemples, le projet Access bien entendu, mais nous nous faisons fort d'aider en fait l'ensemble des acteurs pour renforcer encore cette dynamique au niveau européen. Alors vous allez me dire qu'est-ce qu'on peut faire concrètement. Je crois qu'il y a eu la question de poser. Vous nous challengez. Alors je ne vais pas avoir des réponses toutes faites, très clairement. Bien souvent, quand on parle d'appui, on pense à des appuis financiers. C'est ce qui arrive très très vite. Alors je ne suis pas venue avec un carnet de chèques. D'ailleurs, je représente l'Agence régionale d'innovation et de prospection internationale. Et j'ai l'honneur de parler au nom de la région. Donc moi, je n'ai pas le carnet de chèques de la région. Mais en tout cas, la région a pris conscience de ces enjeux. Et pour exemple, c'est le soutien qui sera apporté au projet d'institut quantique par la région et par l'État, puisque ce projet est inscrit dans le contrat plan État-région. Donc ça, c'est quelque chose de très, très concret. Au-delà de ça, j'ai envie de dire qu'est-ce que nous pouvons faire ensemble? De quoi avez-vous besoin? Et j'ai aussi relevé à plusieurs reprises cette nécessité de faire fructifier l'intelligence collective. Et ça, nous aimons bien. Je crois que ça s'est coupé. Non, c'est bon. Nous aimons bien. Et c'est vraiment le sens dans lequel nous souhaitons travailler. Et nous travaillons maintenant depuis plusieurs années avec l'ensemble des acteurs d'un domaine en particulier. Alors on a démarré ce genre d'approche, ce type d'approche autour de l'intelligence artificielle, où nous partions de loin. Nous étions passés à côté d'un appel à projet pour des instituts interdisciplinaires d'IA, et l'ensemble des présidents universitaires ont interpellé la région. Comment pouvez-vous nous aider? Le président de région a pris le pari d'aider les acteurs académiques dans une logique de faire avancer tout l'écosystème régional. Donc pas uniquement académique, mais bien de le connecter aussi au monde économique. Et je pense qu'à un moment donné, il y a ces ponts à créer. On a beaucoup parlé de start-up. Voilà, c'est un premier pas vers cette connexion du monde académique au monde économique. Et donc nous avons travaillé tous ensemble pour écrire une feuille de route. Donc écrire le projet à déployer pour rendre la région plus visible sur un sujet qui à l'époque était l'intelligence artificielle. Eh bien, c'est tout simplement le même type de démarche que l'on peut faire. On a commencé à le faire sur d'autres sujets également. Et donc, c'est pour ça que je dis que rien n'est écrit. C'est quelque chose à travailler ensemble, sans nul doute. Alors, pour l'instant, on ne parle pas beaucoup de quantique, très concrètement. Vous parliez d'événements, qu'est-ce qu'on peut faire? C'est vrai que demain a lieu un événement majeur quand on parle d'innovation, qu'on parle de politique régionale, politique économique. C'est l'événement 360 Grand Est. Pour ceux qui ne seraient pas inscrits, n'hésitez pas. Plus de 2000 participants déjà attendus. Le quantique ne fait pas partie des sujets abordés. On parlera d'intelligence artificielle, on parlera de cybersécurité, de transition environnementale, industrielle, et ainsi de suite. Bien, prenons le pari qu'en travaillant tous ensemble, eh bien, l'année prochaine, nous parlerons du quantique. Nous parlerons du quantique au prochain 360. Nous en parlerons lors d'un autre rendez-vous qui a lieu ce soir, qui est un rendez-vous à l'échelle européenne, où nous recevons l'ensemble des décideurs politiques et les principaux faiseurs opérationnels pour aborder les politiques en matière de développement économique et il y aura un focus sur le sujet du numérique. Donc la région se mobilise pour rendre visibles ces acteurs en étant connectés avec nos partenaires européens. Et donc ça fait partie du champ des possibles pour le quantique. Et je terminerai peut-être par un exemple, en rebond à ce qui a été dit autour du projet Access, qui montre aussi ce que la région est capable de faire. C'est un projet dans le domaine de l'intelligence artificielle, où dans le cadre du plan qui a été construit, il y avait une ambition de rendre visible un projet au niveau européen et vraiment de l'appuyer. Ce projet s'appelle Clinova. Il a pour objectif de développer un hub de solutions en intelligence artificielle pour élaborer des thérapies innovantes dans un certain nombre de maladies. Ce projet, c'est un projet aujourd'hui à 100 millions d'euros qui est soutenu par le Luxembourg, qui est soutenu par le Bade-Württemberg, qui est soutenu par la Sarre et bien entendu la région Grand Est, et nos amis wallons vont nous rejoindre. Donc ça montre que le champ des possibles est là. Après, c'est un travail à mener tous ensemble, tout simplement. Voilà ce que je souhaitais partager avec vous aujourd'hui. Et puis je terminerai peut-être par un clin d'œil. Alina, particulièrement. Il y a un sujet auquel je suis très attachée, qui est celui de la représentativité des femmes dans le monde du numérique. Je pense que c'est une nécessité. Ce n'est pas juste un nice to have, mais c'est un must have. Et en échangeant avec Alina, j'ai vraiment eu une agréable surprise. C'est que quand on parle quantique, eh bien, il y a bon nombre de femmes qui sont actives dans ce domaine dans la région Grand Est. Et je tenais vraiment à saluer ce point et puis encourager les jeunes filles et puis les femmes à rejoindre cette aventure du quantique. Voilà.
Merci beaucoup Isabelle. J'invite surtout Inès, Kaotar, Rachel de nous rejoindre et Stéphanie aussi de nous rejoindre sur la scène. Et je vous demande vraiment de les applaudir parce qu'elles sont vraiment les femmes du quantique de la région Grand Est. Donc merci encore à elles d'être là avec nous et bien sûr Isabelle. Donc je peux vous dire aujourd'hui, parce qu'on n'a pas parlé des statistiques, mais notre événement, ça a représenté 40% des femmes et 60% des hommes. Et je souhaite féliciter notamment mon équipe aussi, et puis l'INSA Strasbourg et QMat, en fait, de cette organisation. Et applaudissons-les. Merci. Et puis, j'ai commencé en anglais, je vais finir en français. Voilà. Et puis, je vais finir par vous remercier pour votre curiosité d'être là avec nous. Et comme tout le monde l'a dit aujourd'hui, à peu près tout ce qu'on fait dans la vie, ça va être lié au quantique. Donc, on va pas vous dire au revoir, on va vous dire à bientôt. Voilà. Merci.